In the quest to find another Earth, scientists have turned their gaze to Proxima B, our closest exoplanet neighbor. But the James Webb Space Telescope's latest image reveals a world that's both tantalizingly similar and alarmingly different from our own.
We have found a planet around the nearest star, Proxima Centauri. So this discovery didn't happen, obviously, from one day to the next.
So what's the closest Earth-like planet you think is worth visiting? How hard is it?
Proxima Centauri. It's over 4 light years away, and we can't travel at the speed of light. Today, there are plans that have planted the seed that shift this line, how we could send probes there.
The James Webb Space Telescope, humanity's most advanced eye in the sky, has recently captured the clearest image of Proxima B to date. This groundbreaking achievement marks a significant milestone in our understanding of exoplanets and the potential for extraterrestrial life. The unprecedented clarity of this image allows scientists to study Proxima B's features in detail, offering new insights into its composition and environment. As we delve deeper into the mysteries of Proxima B, we find ourselves at the intersection of hope and adversity. The planet's proximity to Earth makes it an enticing target for exploration, yet its harsh conditions pose formidable challenges. In the following sections, we'll explore the complex nature of Proxima B and the technological marvels that have made this discovery possible, unraveling the enigma of our cosmic neighbor. Our closest exoplanet neighbor, Proxima B, our closest exoplanet neighbor, orbits the star Proxima Centauri at a distance of just 4.2 light-years from Earth. This proximity makes it a prime target for scientific study and exploration. Despite its relative closeness, Proxima B remains shrouded in mystery, presenting a complex puzzle that challenges our understanding of planetary formation and habitability. Recent measurements have revealed intriguing details about Proxima B's physical characteristics. The planet has a minimum mass that is 17% greater than Earth's, suggesting it may be more Earth-like than previously estimated. This increased mass could indicate a rocky terrestrial composition similar to our own planet. Adding to its allure, Proxima B completes an orbit around its star every 11.2 Earth days, a remarkably short period that speaks to its close proximity to Proxima Centauri. One of the most exciting aspects of Proxima B is its location within the habitable zone of its star. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. This concept is crucial in the search for potentially habitable worlds, as liquid water is considered essential for life as we know it. The significance of Proxima B's position within the habitable zone cannot be overstated. It raises the tantalizing possibility that this distant world could harbor liquid water and, by extension, potentially support some form of life. This prospect has ignited the imagination of scientists and the public alike, fueling dreams of discovering life beyond our solar system. Recent advancements in technology have allowed for more precise measurements of Proxima B's characteristics. The espresso spectrograph, a powerful instrument designed to detect and study exoplanets, has provided new insights into Proxima B's nature. These latest measurements suggest that Proxima B could indeed be a rocky, terrestrial planet similar to Earth, further enhancing its potential for habitability. However, the story of Proxima B is not without its challenges. The planet's close proximity to its star, while allowing it to reside within the habitable zone, also presents significant obstacles. Proxima Centauri, a red dwarf star, is smaller and cooler than our Sun, but it poses unique threats to its planetary companion. The intense radiation emitted by Proxima Centauri raises serious concerns about Proxima B's ability to retain an atmosphere. Without a protective atmospheric layer, the planet's surface would be exposed to harmful stellar radiation, potentially making it inhospitable for life as we understand it. This close dance between planet and star creates a precarious balance, where the very factors that place Proxima B in the habitable zone also threaten its potential to support life. This tension between hope and adversity exemplifies the complex nature of exoplanet research. On one hand, Proxima B's Earth-like mass and position within the habitable zone fuel optimism about its potential to harbor life. On the other hand, the harsh realities of its stellar environment present significant challenges to its habitability. The harsh realities of Proxima B's environment. At the heart of Proxima B's story lies its host star, Proxima Centauri. This celestial body is a red dwarf, a class of stars that differs significantly from our Sun. Red dwarfs are smaller, cooler, and far more numerous than stars like our own. While their cooler temperatures might seem advantageous for nearby planets, the reality is far more complex. Proxima Centauri's diminutive size and lower temperature mean that its habitable zone, the region where liquid water could potentially exist on a planet's surface, is much closer to the star than in our solar system. This proximity creates a host of challenges for Proxima B, our nearest exoplanet neighbor. One of the most significant consequences of Proxima B's close orbit is the likelihood of tidal locking. This phenomenon occurs when a planet's rotation becomes synchronized with its orbit, causing one side to always face its star while the other remains in perpetual darkness. The implications of this are profound. Imagine a world where one hemisphere basks in eternal daylight while the other never sees its sun. This tidal locking leads to extreme temperature variations across Proxima B's surface. The side facing Proxima Centauri likely experiences scorching heat, potentially hot enough to melt rock. In contrast, the dark side might be locked in a permanent frigid night. Between these two extremes, there could be a narrow band, often called the terminator line, where temperatures might be more moderate. This twilight zone represents one of the few areas where conditions could potentially support life as we know it. However, temperature extremes are just the beginning of Proxima B's environmental challenges. The planet's close proximity to its star exposes it to intense radiation. Red dwarf stars, despite their smaller size, can be incredibly active and prone to powerful flares. These stellar outbursts pose a significant threat to any potential life on nearby planets. In April 2021, astronomers observed a flare from Proxima Centauri that was truly staggering in its intensity. This event was 100 times more intense than any flare recorded from our Sun, demonstrating the volatile nature of Proxima B's cosmic neighborhood. Such powerful flares could strip away a planet's atmosphere over time, leaving its surface exposed to harmful radiation. The radiation environment around Proxima B is further complicated by the star's magnetic activity. Researchers believe that the chaotic surface activity of Proxima Centauri leads to powerful magnetic fields that contribute to the high-energy radiation environment around Proxima B. This constant bombardment of radiation poses a significant challenge to the development and survival of life as we understand it. To put the intensity of this radiation into perspective, consider this. Proxima B experiences solar wind radiation that is approximately 1,000 times greater than what Earth receives. This relentless onslaught of charged particles and high-energy radiation would be devastating to most forms of life familiar to us. Given these harsh conditions, it's natural to question the possibility of life on Proxima B. As one researcher noted, while the idea of a habitable planet orbiting Proxima Centauri is captivating, the reality seems far from hospitable. The combination of extreme temperatures, tidal locking, and intense radiation creates an environment that appears hostile to life as we know it. Another scientist remarked, "It's hard to imagine life surviving such intense radiation without specialized shelter." This statement encapsulates the challenge facing any potential life on Proxima B. To survive in such an environment, organisms would need to develop extraordinary adaptations or find ways to shelter from the constant barrage of radiation. Yet, it's crucial to remember that our understanding of life and its potential forms is limited to what we've observed on Earth. The very challenges that make Proxima B seem inhospitable also push us to expand our concepts of habitability and life itself. Could there be forms of life that thrive in conditions we consider extreme? Might the unique environment of Proxima B foster types of life entirely different from what we're familiar with? Technological marvels, overcoming the odds. In the face of Proxima B's extreme environment, humanity has risen to the challenge with remarkable technological innovations. At the forefront of this endeavor stands the James Webb Space Telescope, JWST, a marvel of engineering that has revolutionized our ability to study distant exoplanets. The JWST represents a quantum leap in space observation technology. Its advanced infrared imaging capabilities allow astronomers to peer through cosmic dust and gas, revealing details of exoplanets that were previously hidden from view. This breakthrough has been particularly crucial in our study of Proxima B, providing unprecedented clarity in imaging our closest exoplanet neighbor. What makes the JWST so exceptional in its ability to study Proxima B? The answer lies in its sophisticated suite of instruments and its strategic position in space. Orbiting the Sun about 1 million miles from Earth, the JWST is shielded from the interference of our planet's atmosphere and the heat of the Sun. This optimal positioning, combined with its large mirror and sensitive detectors, allows it to capture the faintest signals from distant worlds. The JWST's capabilities extend beyond mere imaging. Its instruments can analyze the light passing through an exoplanet's atmosphere, providing crucial data about its composition. This technique, known as spectroscopy, has the potential to detect biosignatures, chemical markers that could indicate the presence of life. While the JWST has captured the headlines, it's not the only technological marvel contributing to our understanding of Proxima B. The espresso spectrograph, installed on the Very Large Telescope in Chile, has played a pivotal role in refining our knowledge of this enigmatic world. Espresso's capabilities allow it to split light from Proxima B into its component wavelengths, enabling detailed analysis of the planet's characteristics. The precision of Espresso's measurements is truly astounding. Francesco Pepe, a co-author of the Espresso study, expressed satisfaction with the instrument's performance, stating, "We're really pleased that Espresso can produce even better measurements." This improved accuracy has allowed scientists to refine their estimates of Proxima B's mass and orbit, bringing us closer to understanding its true nature. Looking to the future, an even more ambitious project is on the horizon, the Starshot Initiative. This groundbreaking concept aims to send a fleet of tiny spacecraft to Alpha Centauri, potentially allowing us to study Proxima B up close. The Starshot project faces significant challenges, including the need for 100 gigawatts of power from 100 million lasers to propel a probe at 20% the speed of light. Despite these hurdles, the potential rewards are immense. If successful, Starshot could revolutionize our approach to space exploration, reducing travel time to Proxima B from thousands of years to mere decades. The technological challenges of the Starshot initiative are formidable. The spacecraft designed for this mission must reflect 99.99% of incoming light to prevent overheating during its journey. Additionally, the Starshot team is exploring the use of adaptive optics to overcome atmospheric interference, allowing for a more focused laser beam on the spacecraft. These innovations push the boundaries of what's currently possible in space technology. Each of these technological marvels, the JWST, Espresso, and the proposed Starshot initiative, represents a testament to human ingenuity and our relentless pursuit of knowledge. They allow us to overcome the vast distances and harsh conditions that separate us from Proxima B, bringing us closer to understanding our cosmic neighborhood. The search for life, hope amidst adversity. Proxima B stands as a testament to the complexity of our cosmic neighborhood. Its status as our closest exoplanet neighbor, coupled with its location within the habitable zone of Proxima Centauri, makes it a prime candidate for potential life. However, the harsh realities of its environment present significant challenges to this possibility. The planet's Earth-like mass and position within the habitable zone initially fueled optimism about its potential to harbor life. These factors suggest that Proxima B could have a rocky composition and might support liquid water on its surface, two crucial elements in our search for habitable worlds. Yet, the very proximity to its star that places Proxima B in the habitable zone also exposes it to extreme conditions that could render it inhospitable. The intense radiation from Proxima Centauri, particularly the powerful flares observed in recent years, poses a significant threat to any potential life on the planet. This constant bombardment of high-energy particles could strip away Proxima B's atmosphere over time, leaving its surface exposed to harmful radiation. The likely tidal locking of the planet further complicates matters, creating extreme temperature variations across its surface. In the midst of these challenges, a recent discovery has reignited interest in the search for life beyond our solar system. Astronomers detected a mysterious signal from the Alpha Centauri system at a frequency of 982.07 MHz. This finding has sparked speculation about the possibility of intelligent life in our cosmic backyard. While some experts suggest that the signal might originate from manufactured equipment, others remain cautiously optimistic that it could indicate extraterrestrial intelligence. The discovery of this signal serves as a stark reminder of the potential for groundbreaking discoveries in our quest to understand the universe. It underscores the importance of continued exploration and study of nearby star systems, including Proxima Centauri and its intriguing exoplanet, Proxima B. Studying Proxima B offers a unique opportunity to refine our understanding of what makes a planet truly habitable. By examining how extreme conditions affect the potential for life, scientists can expand their criteria for habitability beyond Earth-like standards. This approach could lead to new insights into the resilience and adaptability of life in diverse environments. The harsh conditions on Proxima B challenge us to reconsider our definitions of life and habitability. Could there be forms of life that thrive in environments we consider extreme? Might the unique conditions on Proxima B foster types of life entirely different from what we're familiar with on Earth? These questions push the boundaries of our scientific understanding and imagination. As we gather more data about Proxima B, we are compelled to balance scientific possibility with the harsh realities of space environments. While the planet's proximity and location within the habitable zone offer hope, the intense radiation and extreme temperature variations present significant obstacles. This delicate balance between optimism and realism drives the continued exploration and study of our nearest exoplanet neighbor. The James Webb Space Telescope's recent capture of the clearest image of Proxima B to date marks a significant milestone in our understanding of this enigmatic world. This technological achievement allows scientists to study Proxima B's features in unprecedented detail, offering new insights into its composition and environment. Such advancements bring us closer to unraveling the mysteries of our cosmic neighbor and potentially answering the age-old question: are we alone in the universe? Future prospects. The road to Proxima B. The journey to Proxima B represents one of humanity's greatest challenges in space exploration. With current technology, reaching our nearest exoplanet neighbor would take approximately 6,000 years. This staggering time frame underscores the vast distances that separate us from even our closest cosmic neighbors. It's a stark reminder of the limitations we face in our quest to explore the universe beyond our solar system. However, human ingenuity continues to push the boundaries of what's possible. Enter the Starshot Initiative, an ambitious project that aims to drastically reduce the travel time to Alpha Centauri, the star system that hosts Proxima B. This groundbreaking endeavor targets a journey of just 22 years, a fraction of the time required by conventional spacecraft. The Starshot project proposes to achieve this feat through a revolutionary approach to space travel. It plans to utilize a fleet of small probes, each about 10 meters in diameter, propelled by powerful lasers. These spacecraft would travel at an astonishing 20% of the speed of light, enabling rapid exploration of Proxima B and its surroundings. The scale of this undertaking is truly mind-boggling. The Starshot Initiative requires an immense power output of 100 gigawatts, equivalent to the entire electricity consumption of the United States. However, this enormous power would only need to be sustained for about 10 minutes to launch the probes on their interstellar journey. Once launched, these probes would embark on a 2-decade journey across the cosmic void. Upon reaching Alpha Centauri, they would have approximately 2 hours to gather data and transmit it back to Earth. This transmission would then take an additional 4 years to reach us, adding to the complexity of interstellar communication. The potential impacts of successfully exploring Proxima B extend far beyond the realm of scientific discovery. Such an achievement would mark a new chapter in human history, fundamentally altering our perspective on our place in the universe. It would provide unprecedented insights into the nature of exoplanets, potentially answering age-old questions about the prevalence of life beyond Earth. From a philosophical standpoint, the exploration of Proxima B challenges us to reconsider our role as a species. It pushes us to contemplate the possibilities and responsibilities that come with becoming an interstellar civilization. The knowledge gained from such a mission could reshape our understanding of planetary formation, evolution, and the conditions necessary for life to emerge and thrive. However, as we contemplate the exploration and potential colonization of other worlds, we must also grapple with significant ethical considerations. The idea of altering another planet's environment raises complex questions about our rights and responsibilities as cosmic explorers. Should we intervene in the natural processes of other worlds? What precautions should we take to prevent contamination or unintended consequences? These ethical dilemmas become even more pronounced if we were to discover any form of life on Proxima B, no matter how primitive. The potential impact on indigenous life forms, even microbial ones, must be carefully considered in any exploration or colonization efforts. A new chapter in space exploration. The exploration of Proxima B marks a new frontier in our quest to understand the universe. This enigmatic world, both tantalizing and treacherous, challenges our notions of habitability. Its Earth-like mass and position in the habitable zone offer hope, while its harsh radiation environment and extreme temperatures present significant obstacles. Technological marvels like the James Webb Space Telescope and espresso spectrograph have revolutionized our ability to study this distant world, providing unprecedented clarity and detail. The potential Starshot initiative represents humanity's ambition to bridge the vast distances of space. As we continue to unravel Proxima B's mysteries, we expand our understanding of what makes a planet truly habitable and push the boundaries of our technological capabilities. This journey of discovery reflects humanity's enduring drive to explore the unknown, even in the face of seemingly insurmountable challenges.
What a feast of astronomical activity. These gigantic black holes lurk at the center of galaxies. We have one right in the center of the Milky Way galaxy.
That's right. Time and space are like a fabric, like rubber, like a trampoline net. However, if you stretch the trampoline net so much, it can rip, perhaps. And perhaps you can turn this trampoline net into a pretzel and allow yourself to go backwards in time.
We physicists have waited 100 years since 1916 for this photograph.
For over a century since Einstein first predicted their existence in 1916, the scientific community and enthusiasts alike have been captivated by the allure of capturing an actual photograph of a black hole. These cosmic giants, powerful beyond comprehension yet invisible to the naked eye, stir both awe and mystery in our quest for understanding the universe. As we explore these massive beasts of the cosmos, we delve into how something so immensely powerful can remain virtually unseen, hidden within the very fabric of space-time itself. Join us as we uncover the secrets of these mysterious phenomena.
Now we've got it in the bag. We've actually photographed the silhouette, the shadow of a black hole. But that's just the
Historical context and theoretical foundations. Albert Einstein's groundbreaking theory of general relativity in 1916 revolutionized our understanding of gravity and the cosmos, predicting phenomena that even he could barely imagine, including black holes. These theoretical voids in the fabric of space-time, where gravity's pull is so strong that nothing, not even light, can escape, remained a mathematical curiosity for decades. It wasn't until the 1960s that black holes shifted from theoretical constructs to observable realities. Astronomers studying the Cygnus constellation observed a blue star emitting unusual X-rays and behaving erratically around an invisible partner. This led to the discovery of Cygnus X1, a compelling candidate for a black hole, providing the first physical evidence that these cosmic behemoths were not just theoretical fantasies, but real astronomical entities in our universe. First discovery and characteristics of black holes. The story of black holes took a dramatic turn with the discovery of Cygnus X1. In the 1960s, astronomers studying the Cygnus constellation were intrigued by an unusually bright blue star emitting X-rays at an extraordinary rate. This was no ordinary celestial body. It was a stellar phenomenon behaving in ways that defied initial understanding. Further investigation revealed that these X-rays were not just emanating on their own, but were being intensely pulled into a nearby invisible object, which we now know as a black hole, This discovery was pivotal because it provided the first concrete evidence of black holes' existence, confirming Albert Einstein's theoretical predictions. Cygnus X1 exhibited properties that were both fascinating and terrifying. It shone with a luminosity about 14 times that of our Sun, yet its gravitational pull was so strong that not even light could escape it, rendering the black hole invisible and justifying its name. This immense gravitational force is crucial for understanding why black holes are such a significant find in the cosmos. They are not merely vacuums in space, but regions where gravity reshapes the very fabric of reality. This blend of visible indicators and invisible forces made Cygnus X1 a landmark in astronomical studies and sparked a renewed interest in probing deeper into the nature of black holes, research evolution, and modern understanding. Over the decades, our understanding of black holes has transformed dramatically. From theoretical predictions to tangible evidence, the journey culminated in a groundbreaking moment in 2021 when scientists captured the first clear photograph of a black hole located in the M87 galaxy. This image wasn't just a snapshot. It was a major leap in cosmic photography achieved by linking telescopes worldwide to create a planet-sized interferometer, which provided the necessary resolution to see the unseeable. The photograph itself revealed much more than expected. It gave us a direct look at the event horizon, or the point of no return, where gravitational pull becomes so strong that not even light can escape. This allowed astronomers to confirm several theoretical predictions about black holes' behavior and structure. By observing the glowing gas orbiting at the edge of the event horizon, researchers could measure the black hole's massive influence on its surroundings, offering new insights into how matter behaves in such extreme environments. This not only validated some of Einstein's predictions about general relativity, but also opened new avenues for understanding the fundamental laws of physics in the most extreme conditions known in the universe. The layers of a black hole. Diving deeper into the anatomy of a black hole reveals a complex structure composed of distinct layers, each playing a critical role in its function and behavior. The outermost layer, known as the event horizon, is famously termed the point of no return. It marks the boundary beyond which nothing, not even light, can escape the gravitational pull of the black hole. This layer defines the visible outline of the black hole and acts as a gateway to its mysterious inner workings. Moving closer to the core, we encounter the photon sphere. This is a not-so-well-known layer where gravity is so strong that photons, particles of light, are forced into orbital paths around the black hole. Here, light bends around the black hole in a mesmerizing cosmic dance, creating loops of brilliant light that can sometimes be observed with sophisticated telescopes. The photon sphere is crucial for astronomers trying to see and study black holes indirectly by observing how light behaves in this extreme environment. At the very heart of a black hole lies the singularity, a point where the laws of physics as we know them break down. In this region, matter is crushed to infinite density, and the gravitational pull is infinitely strong. The singularity represents one of the greatest mysteries in modern physics. It's where our understanding of gravity, space, and time is challenged, and where current theories reach their limits. Each layer of a black hole, from the event horizon to the singularity, not only contributes to its intriguing nature, but also offers a unique playground for testing the theories of physics in extreme conditions. The nature and dangers of black holes. Black holes are not just fascinating scientific phenomena, they are also incredibly dangerous regions of space. At the heart of their danger is their intense gravitational pull, a force so strong that nothing, not even light, can escape once it crosses the event horizon. This boundary marks the point of no return. For any object unfortunate enough to get too close, the outcome is both dramatic and fatal. This leads us to the gruesome concept of spaghettification. Imagine you're falling feet first into a black hole. The gravitational pull on your feet would be significantly stronger than on your head, stretching you longer and thinner like spaghetti. This stretching happens because different parts of your body experience different intensities of gravity. Eventually, this effect becomes so extreme that it tears apart anything caught in its grasp, atom by atom. The perils of black holes extend beyond the immediate destruction of material objects. Their presence can disrupt nearby stellar environments, drawing in and accumulating gas, dust, and other celestial debris in a swirling accretion disk. This accumulation can lead to energetic emissions and powerful jets that reshape their cosmic neighborhood. Thus, the very nature of black holes as regions of extreme gravity makes them not only fascinating to study, but also incredibly hazardous to anything within their reach. Recent photographic breakthroughs. In a groundbreaking achievement, scientists have recently managed to capture the first clear images of a black hole, specifically the M87 black hole. This monumental event in astrophysics not only confirms the existence of black holes, but also allows us to peek into the dynamic processes that govern these enigmatic features of our universe. By stitching together multiple photographs taken over several nights, researchers have developed a more comprehensive view of the black hole structure. These images reveal fascinating details about the black hole's behavior, particularly how matter and light behave around this extreme gravitational force. This insight is crucial as it helps scientists understand the accretion processes and the emission of powerful jets that extend thousands of light years into space. The ability to visually observe these phenomena provides unprecedented information, transforming our theoretical knowledge into tangible, observable facts. This data is vital for testing the limits of our current physical theories and potentially guiding us towards new discoveries in black hole dynamics and the fundamental laws of physics. Black hole theories and spinning black holes. In 1963, Roy Kerr revolutionized our understanding of black holes with his groundbreaking model that described not just any black hole, but those that spin. This concept introduced us to the idea of rotating black holes, which differ significantly from the non-spinning versions predicted by earlier theories. Kerr's model proposes that the space around these spinning black holes twists along with them, leading to the formation of something known as the ergosphere. This region, lying just outside the event horizon, is where the effects of the black hole's spin are most pronounced. Matter and radiation can enter the ergosphere and receive energy from the black hole's rotation, potentially being flung out at great speeds. The implications of Kerr's model stretch even further with the theoretical possibility of the Einstein-Rosen bridge, commonly referred to as a wormhole. This hypothetical feature suggests a tunnel-like pathway through space-time, facilitated by the unique structure of spinning black holes. Theoretically, these bridges could connect two distant points in the universe, or potentially link to parallel universes. While the existence of such wormholes remains speculative, the discussion it sparks among physicists and the general public alike continues to fuel both scientific inquiry and popular fascination with the cosmos. Wormholes and interstellar possibilities. Wormholes capture the imagination as potential shortcuts through the vastness of space-time, offering hypothetical routes that could connect distant or even parallel universes. Derived from Einstein's equations, these intriguing structures are theorized to form tunnels between disparate points in the cosmos, potentially allowing for instantaneous travel across astronomical distances. However, the science behind wormholes is fraught with challenges. Current understanding suggests that while they may theoretically exist, wormholes would likely be highly unstable, collapsing too quickly for anything to pass through without extraordinary amounts of negative energy, something not currently understood to exist in the necessary quantities. This instability has led many scientists to approach the concept of practical wormhole travel with skepticism, maintaining a cautious perspective on the feasibility of using these cosmic phenomena as pathways for interstellar travel. Despite these hurdles, the study of wormholes continues to be a vibrant area of theoretical physics, pushing the boundaries of our understanding of the universe. Superstring theory and its implications. Superstring theory offers a groundbreaking perspective on the unification of the universe's most fundamental forces. This theory suggests that what we perceive as particles are actually tiny, vibrating strings, each resonating at specific frequencies. Unlike traditional particle physics, superstring theory requires a universe with 10 dimensions, far beyond the 4 dimensions of space and time that we experience daily. These additional dimensions aren't just theoretical quirks. They are essential for the mathematics of the theory to work properly, providing a framework that could potentially explain every force and particle in the universe. This bold idea not only bridges the gap between Einstein's theory of general relativity, which governs the cosmos at the largest scales, and quantum mechanics, which reigns over the smallest, but it also offers explanations for phenomena that otherwise defy classical explanations. For instance, superstring theory could elucidate the nature of black holes, which challenge our understanding of both gravity and quantum mechanics. By viewing these cosmic puzzles through the lens of superstring theory, physicists hope to unlock answers to some of the most profound questions about the structure and origins of the universe, experimental challenges, and theoretical developments. Studying black holes presents unique challenges to scientists, primarily because these cosmic phenomena do not emit light, making them invisible to traditional observation methods. Researchers must instead rely on indirect methods, such as observing the gravitational effects black holes have on nearby stars and gas clouds. This indirect approach adds layers of complexity and uncertainty to their studies. Further complicating the study of black holes is the theoretical framework of superstring theory. This advanced theory suggests that all fundamental particles are not point-like dots, but rather tiny vibrating strings. Superstring theory is a leading candidate in the quest to unify Einstein's theory of general relativity with quantum mechanics. However, it posits the existence of 10 dimensions, 6 beyond the 3 spatial dimensions and 1 time dimension we experience daily. These extra dimensions are theorized to be compact and rolled up so tightly that they are beyond our current capability to observe directly, posing a significant hurdle for empirical validation. The unstable properties of theoretical constructs like wormholes add another layer of complexity. Wormholes, predicted by the equations of general relativity under specific conditions, are passages through spacetime that could, in theory, connect distant parts of the universe or different universes altogether. However, the inherent instability of these wormholes and the extreme conditions likely found at their entrances, such as intense radiation and crushing gravitational forces, make them difficult to study or even confirm their existence scientifically. These challenges mean that much of what we understand about black holes and related phenomena remains speculative, relying on advancing theoretical physics and improving observational technologies to bring these cosmic mysteries into clearer view. The Big Bang and beyond in string theory. String theory offers a fascinating twist on the Big Bang theory, suggesting that what we perceive as the universe's beginning might actually be far more complex. According to this theory, our universe could potentially be the product of 2 separate universes colliding, or a universe birthing another, akin to a cosmic child emerging from its parent. This interconnection between universes is conceptualized through what's known as wormholes, which are theorized as cosmic tunnels linking disparate parts of the universe or even different universes altogether. The implications of this are staggering. If wormholes are real and stable enough to connect different realms of space-time, our current understanding of our place in the cosmos could be fundamentally altered. It raises the possibility that what we consider black holes might actually be gateways or bridges to other dimensions or distant parts of our universe. This leads to an even more bewildering possibility. Could our entire observable universe be inside a black hole located in a much larger universe? Such a scenario would redefine concepts of beginning and end and what it means to exist in this universe. As we continue to explore these profound questions, the mysteries of the cosmos keep our curiosity piqued, pushing the boundaries of our understanding of the very fabric of reality. We hope you found these facts intriguing. If you've heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery. While you're still here, feel free to click on other videos you will see on your screen right now.
Like any star, it will run out of fuel in its core, and it starts changing, it starts bloating.
It's very unstable, it's about to explode.
No, it's about to, give me the timescale for that.
The thing is, it could be tomorrow.
The entire universe will be aware of this one explosion.
Betelgeuse, the colossal red supergiant blazing at the shoulder of Orion, just experienced a staggering 150% surge in brightness, an enigmatic pulse that has astronomers buzzing with excitement. This cosmic titan has a history of erratic behavior, with recent outbursts suggesting it could be on the brink of a supernova explosion. But when will it happen? What does this mean for our understanding of the universe? As we delve into the mysteries surrounding this giant, we'll uncover how Betelgeuse's unprecedented brightness changes are rewriting what we know about stars and bringing us closer to an astronomical spectacle that could light up our sky for weeks. The recent brightening surge. In a recent and stunning astronomical event, the James Webb Space Telescope has captured a significant increase in the brightness of Betelgeuse, one of the most well-known stars in our night sky. This red supergiant, typically noted for its steady glow on the shoulder of the Orion constellation, has recently surged to become the seventh brightest star visible from Earth. The brightness of Betelgeuse has peaked at an astonishing 150% above its usual luminosity. This sudden and unexpected brightening of Betelgeuse offers a unique spectacle for both amateur stargazers and professional astronomers. Positioned in a constellation familiar to many, its enhanced brilliance makes it an even more striking feature in the night sky. The increased brightness is not just a trivial change. It represents significant and dynamic processes occurring in the star's life cycle. Such a surge in luminosity could be linked to changes in the star's surface temperature, size, or radiative processes, showcasing the unpredictable nature of these celestial giants. As the star currently ranks as the seventh brightest, its prominence in the sky is a call to observers and scientists to watch closely. Each observation and data point collected helps in piecing together the complex life story of stars like Betelgeuse. The James Webb Space Telescope, with its advanced capabilities, continues to monitor these changes, providing crucial insights into the behavior of stars on the brink of their evolutionary shifts. This event not only enriches our understanding of stellar dynamics, but also enhances the nightly spectacle for skywatchers around the globe. Supernova anticipation. As the enigmatic red supergiant Betelgeuse continues to dazzle stargazers and astronomers alike, anticipation is mounting over the possibility of it going supernova, a stellar explosion that could offer a spectacle unlike any other seen in our lifetimes. Betelgeuse, a behemoth star nearing the end of its life, has sparked a wave of speculation due to its unusual and dramatic fluctuations in brightness. This has led many to wonder, are we on the brink of witnessing a supernova? Experts in the field are closely monitoring Betelgeuse, predicting that it might explode into a supernova within the next few decades. This potential timeline, however, contrasts starkly with NASA's more conservative estimate, which suggests that Betelgeuse's supernova event may not occur for another 100,000 years. This disparity in predictions underscores the complexities and uncertainties inherent in studying such colossal celestial phenomena. The prospect of Betelgeuse's supernova has not only captivated the scientific community, but has also permeated popular discussions. The idea that we could soon witness one of the most significant events in our galaxy, an event so bright that it could outshine the moon and be visible during daylight hours, stirs a blend of excitement and awe. This anticipation is further fueled by our limited understanding of supernovae, as each observation provides critical data that can redefine what we know about the life cycle of stars. Thus, the watchful eyes of the world remain fixed on Betelgeuse, eagerly awaiting any signs that may hint at its imminent transformation. Whether this spectacular event occurs in the near future or millennia from now, the ongoing study of Betelgeuse offers invaluable insights into the final days of a star's life. Historical brightness patterns. Betelgeuse's erratic luminary ballet has fascinated skywatchers across the millennia. From the indigenous Australians to the ancient Greeks, the star's periodic brightening and fading have been meticulously observed and documented, embedding Betelgeuse deeply into cultural lore and astronomical study alike. Traditionally, this red supergiant exhibited a predictable brightness cycle lasting approximately 400 days. However, recent observations have painted a different picture, revealing a shift to a much shorter 130-day cycle. This significant change in Betelgeuse's behavior marks an atypical deviation from its historic patterns. What could possibly cause such a dramatic alteration in its cycle? This question captivates astronomers and adds a layer of mystery to an already enigmatic celestial body. The shift suggests an underlying change in the star's internal processes or external influences that we are yet to fully understand. The implications of these rapid cycles are profound, both for our theoretical understanding of stellar physics and for the practical monitoring of Betelgeuse. As we continue to observe this star, each cycle of brightening and dimming could bring us closer to unraveling the secrets of its celestial mechanics and perhaps predicting its ultimate fate. For now, the rapid changes serve as a celestial puzzle, connecting the curiosity of ancient civilizations with the high-tech investigations of modern astronomy. The Great Dimming Event. In late 2019, the astronomy community was abuzz as Betelgeuse, one of the most well-known stars in the night sky, began to exhibit some highly unusual behavior. This red supergiant star, famous for its brilliant reddish hue and prominent position in the Orion constellation, unexpectedly dimmed by an astonishing 60%. This phenomenon, quickly dubbed the Great Dimming, sparked a wave of speculation among scientists and stargazers alike, many of whom wondered if Betelgeuse was about to go supernova. The dimming was so significant that it was clearly visible even to casual observers, marking a stark change from the star's typically bright appearance. The sudden shift led to numerous theories about the star's imminent death and transformation into a supernova, which would have been a spectacle visible across vast distances in the galaxy. However, as astronomers monitored the star more closely using the world's most advanced telescopes, a different explanation emerged. It was discovered that the Great Dimming was not a sign of impending supernova, but rather the result of a colossal surface eruption on Betelgeuse. This massive explosion had expelled a significant cloud of dust away from the star's surface. The cloud was large enough to obscure the light coming from Betelgeuse, leading to its dramatically reduced luminosity as observed from Earth. This finding was crucial as it not only provided a rational explanation for the dimming, but also offered a rare insight into the kinds of surface activities that can occur on red supergiants like Betelgeuse. The Great Dimming served as a reminder of the dynamic and ever-changing nature of stars, regardless of their age or size. It highlighted the complex interplay of forces operating in these colossal celestial bodies, and how they can lead to spectacular, if misunderstood, events that can momentarily trick us into believing that a star's end is near. Moreover, this episode allowed astronomers to study the mechanisms behind such massive ejections and how they affect the star's behavior and evolution. Understanding these processes is vital for predicting the life cycles of similar stars and preparing for the actual supernova events that one day will light up our skies. Star size and structure. Imagine, if you will, placing Betelgeuse at the center of our solar system. This colossal red supergiant would not merely loom large in our sky. It would engulf it, extending beyond Mars and reaching all the way past Jupiter. This staggering size isn't just for show, it fundamentally affects how Betelgeuse behaves as a star. Betelgeuse is classified as a red supergiant, a type of star that has exhausted the hydrogen in its core and expanded massively as a result. The sheer scale of Betelgeuse can be hard to comprehend. In comparison, if our Sun, a mere speck in size against the backdrop of Betelgeuse, were to suddenly expand to the red supergiant's proportions, it would swallow Mercury, Venus, Earth, and Mars, creating a catastrophic end for our planet. But why does this immensity lead to increased variability? The answer lies in the star's unstable nature. The outer layers of Betelgeuse are only loosely bound to its core due to its vast radius and the relatively low gravitational pull at its surface compared to smaller, more compact stars. This causes the star to pulsate irregularly, significantly changing its brightness as seen from Earth. Additionally, this pulsation allows large convective cells to form and move hot gas from deep inside the star to the surface. When this hot gas reaches the outer layers, it cools and sinks back toward the core, a stellar conveyor belt of sorts that not only stirs the star's atmosphere, but also contributes to the star's periodic dimming and brightening. Understanding Betelgeuse's structure gives astronomers critical clues about the life cycles of red supergiants and how such stars end their lives. Given Betelgeuse's advanced age and bloated size, it stands as a perfect laboratory for studying the final stages before a star goes supernova, offering insights not just into the star itself, but into the broader mechanisms governing stellar evolution, scientific observations and tools. In our quest to unravel the mysteries of the cosmos, the role of advanced astronomical observatories cannot be overstated. Tools like the James Webb Space Telescope, the Hubble Space Telescope, and the Very Large Telescope stand as pillars of modern astronomy, providing us with the essential data needed to decode the behavior and structural changes of stars like Betelgeuse. The James Webb Space Telescope, with its unparalleled infrared sensitivity, allows astronomers to peer into the dusty veils surrounding stars, revealing hidden structures and temperatures that were once beyond our reach. This ability is crucial when studying a star like Betelgeuse, which often shrouds itself in a cloud of its own making. Meanwhile, the Hubble Space Telescope continues to offer invaluable support with its high-resolution capabilities. Its observations have helped track changes in Betelgeuse's size and surface activity over the years, providing a clearer picture of its pulsations and occasional ejections of material. The Very Large Telescope, situated in the arid deserts of Chile, complements these observations with its own unique capabilities. It employs a suite of instruments that can capture high-resolution images and spectra, allowing scientists to observe the star in different light spectrums. This multifaceted approach is essential, as the different wavelengths can tell us about various aspects of the star's surface and atmospheric conditions. The synergy of these observatories has turned Betelgeuse into one of the best-studied stars in our night sky. Each telescope contributes a piece to the puzzle, from mapping the star's vast surface to monitoring its light fluctuations and spectral signatures. This collaborative global effort not only enhances our understanding of Betelgeuse, but also sets the stage for understanding other similar stars across the galaxy. Through the lenses of these powerful observatories, we continue to witness the life story of one of the most intriguing stars visible to the naked eye. Astrophysicist Insights. As we delve deeper into the mysterious life cycle of Betelgeuse, it's crucial to consider the insights from renowned astrophysicist Andrea Dupree of the Harvard-Smithsonian Center for Astrophysics. Dupree's research into this massive red supergiant reveals that Betelgeuse might currently be in a pivotal phase of its stellar evolution. According to her observations, the star could be nearing the end of its core carbon burning stage, a critical phase just before a star transitions into a supernova. The core carbon burning stage is one where a star like Betelgeuse converts its core carbon into heavier elements such as oxygen and magnesium. This process is a precursor to the collapse of the star's core, which could trigger the explosive and spectacular demise known as a supernova. Dupree suggests that this phase could conclude within the next few decades, positioning Betelgeuse on the brink of an epic cosmic event. What's particularly fascinating is how this assessment aligns with the unusual behavior we've observed from Betelgeuse in recent years. The increased frequency and intensity of its brightness fluctuations could be signaling that these internal transformative processes are more advanced than previously understood. This insight not only helps astronomers predict the star's future, but also offers a rare observational opportunity to study the pre-supernova activities in real time, a chance to witness firsthand the final chapters in the life of a star destined to end in a blaze of glory. Historical expectations. In the cosmic arena, our understanding of supernovae has been dramatically reshaped over recent decades. It was once firmly believed that only red supergiants were capable of culminating their stellar life cycles in the dramatic explosions known as supernovae. This view held sway in the astronomical community, grounding our predictions and theories in a framework that seemed unshakable, until 1987, that is. The year 1987 marked a pivotal shift in cosmic perceptions with the surprise supernova of a blue giant. This event sent shockwaves through the scientific community, challenging the long-held belief restricted to red supergiants. The blue giant, significantly hotter and more massive than its red counterparts, defied the expectations by undergoing a supernova, thereby expanding the scope of our understanding of stellar death. This paradigm shift not only widened our horizons regarding which stars could potentially go supernova, but also deepened our curiosity about the life cycles of stars across the spectrum. It underscored a fundamental lesson in astronomy. The universe often holds surprises that defy our expectations and assumptions. Each such event not only adds a new layer to our understanding, but also humbles us, reminding us of the vastness and the mystery of the cosmos that surrounds us. As we continue to observe and study stars like Betelgeuse, we do so with an awareness that what we know is only a fraction of what there is to learn, and what we expect is not always what occurs. Neutrino signals. In the cosmic ballet of the universe, neutrinos, those tiny, nearly massless particles, play a crucial yet often overlooked role. As Betelgeuse inches closer to its dramatic finale as a supernova, it's not just the visible light that will herald its cataclysmic end. Enter the neutrinos, ghost-like particles that rarely interact with matter. These particles could be the earliest messengers of Betelgeuse's impending supernova, providing a crucial heads-up before any visual confirmation is possible. Neutrinos are released in vast quantities during the core collapse of a supernova, a moment when the star's core implodes under its own gravitational pull, moments before the outer layers explode. The fascinating aspect of these particles is their ability to escape from the dense core of the star almost immediately after the collapse begins, traveling through space at nearly the speed of light. This means that neutrinos can reach Earth hours, perhaps even days, before the light from the supernova itself, which can get delayed as it bounces around within the exploding star. For astronomers and astrophysicists, detecting these neutrinos would not only signal that Betelgeuse has finally gone supernova, but also provide invaluable data about the processes occurring within the star's core in its last moments. Around the globe, detectors like the Super Kamiokande in Japan or the Ice Cube Observatory at the South Pole stand ready to catch these elusive particles. The detection of neutrinos from Betelgeuse would be a monumental event, marking only the second time in history that neutrinos from a supernova have been detected, the first being from supernova 1987A, which provided key insights into the life cycle of massive stars. As we monitor Betelgeuse's erratic behavior and shifting luminosity, the watch for neutrinos continues in earnest. These particles may soon serve as the silent heralds of one of the most significant astronomical events of our time, providing a precious few hours warning that a supernova spectacle is about to illuminate the heavens. This early warning could catalyze a flurry of scientific activity, with telescopes across the Earth poised to capture every moment of this stellar explosion in unprecedented detail. Thus, while Betelgeuse's light will fade, its legacy will shine brightly in the annals of astronomical discovery, enhanced by the ghostly glow of neutrinos. Potential impact of supernova. Imagine a day when you look up at the sky and see something brighter than Venus, bright enough to cast shadows on the ground at night. This isn't a scene from a science fiction movie. It's a very real possibility that could occur when Betelgeuse, one of the night sky's most notable stars, goes supernova. Betelgeuse, a massive red supergiant, is nearing the end of its life, and its eventual explosion as a supernova will be a sight to behold. The sheer magnitude of this event is hard to fathom. For context, Venus, often the brightest object in the night sky after the moon, can sometimes be visible during the day. Betelgeuse's supernova, however, will outshine Venus dramatically. This incredible luminosity means that for a period, possibly weeks, Betelgeuse will be visible both during the day and night, turning from a faint star seen in a dark night sky to a celestial beacon visible even under the sun's glare. What's even more fascinating is that despite its formidable appearance and intensity, this supernova poses no direct threat to Earth. The distance of Betelgeuse from our planet ensures that while the spectacle will be stunningly bright, it will not affect our environment or health. Instead, it offers a unique, harmless viewing opportunity that combines the thrill of a once-in-a-lifetime astronomical event with the safety of an ordinary celestial observation. For those worried about potential dangers, it's reassuring to know that while supernovae can emit harmful gamma rays and other energetic emissions, Betelgeuse's distance of about 650 light-years is enough to dilute these effects to negligible levels. The most impactful part of this event for us on Earth will be its breathtaking visibility and the way it lights up the sky, a phenomenon that will allow everyone around the globe to witness astronomical history in the making. In sum, Betelgeuse's dramatic changes offer an unprecedented glimpse into the late stages of red supergiants, refining our knowledge of stellar evolution and supernova mechanisms. By studying its unpredictable behavior, we uncover new insights into the universe's grand cycles, ultimately enriching our understanding of cosmic phenomena. We hope you found these facts intriguing. If you've heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery. While you're still here, feel free to click on other videos you will see on your screen right now.
5, 4, 3, 2, 1, 0. All engine running.
I am Buzz Aldrin.
One small step for man, one giant leap for mankind.
And I was the lunar module pilot on Apollo 11.
Clear. Roger.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11.
Buzz Aldrin, one of the few men to have walked on the moon, possesses unique insights about it thanks to his experience as a lunar astronaut. Later in life, he shared intriguing observations, hinting at mysterious entities or phenomena close enough to be observed on the moon. Does Aldrin's observations challenge conventional knowledge about the moon?
I thought it was a good idea in front of the TV to bounce around and to demonstrate how easy a guy could move around, or a gal could move around on the moon.
Is the moon not what we think it is? Let's learn more about this person. Buzz Aldrin, an astronaut renowned for his academic prowess, including a PhD from MIT, played an instrumental role in the historic Apollo 11 mission as the lunar module pilot. As the pilot of the lunar module, Aldrin had a massive job. He had to land on the moon and then make sure they could get back to Earth safely. This guy wasn't just very intelligent. He was also a top fighter pilot in the Korean War. His mix of brainpower and flying skills was key to the mission's success. But there's more. We're also looking at how Aldrin kept his cool under pressure. Imagine this: you're descending to the moon and you're hit with computer alarms, unknown boulders on the surface, and your fuel's running low. Sounds scary, right? Well, Aldrin, alongside Neil Armstrong, handled it like a pro. His ability to stay calm and make quick, smart decisions was crucial, especially during those tense moments. Thanks to him, the Eagle landed safely on the moon. Stay tuned as we explore the amazing journey of Buzz Aldrin on Apollo 11. The historic moon landing. Guess what? Buzz Aldrin was the second guy to walk on the moon, right after Neil Armstrong. When he stepped onto the moon, he didn't just make history, he became a part of it. But walking on the moon was just one part of his mission. Aldrin was super busy up there, setting up all sorts of science experiments. These weren't just any experiments. They were designed to help us learn everything about the moon, like what it's made of and what its surface is like. Thanks to him, we know a lot more about the moon now. Aldrin also did something really important. He planted the American flag there. This wasn't just about being patriotic. It was a big moment showing what humans can achieve when we aim for the stars. And there's the special thing he did that not many people know about. While he was on the moon, Aldrin took some time for a personal spiritual moment. He actually took communion. It's a reminder that behind all the science and exploration, there's a human touch. Let's talk about how Aldrin described the moon. He called it magnificent desolation. What a way to describe it. It's like he was saying the moon is incredibly beautiful, but also really empty and quiet. It must have been such an unreal experience to stand there in this huge, silent place, so far from Earth. Space sickness experience. Let's dive into something that is about Buzz Aldrin that is not talked about much. His experience with space sickness during the Apollo 11 mission. You know, being an astronaut is not just about the cool stuff like floating in zero gravity or walking on the moon. There are some tough challenges too, and space sickness is definitely one of them. You can compare it with seasickness if you have ever had it before. Now, when Aldrin was up there in space, he actually got really sick. But here's the thing, Back then, nobody really talked about it. It wasn't until later, in his autobiography and some interviews, that Aldrin opened up about this experience. This was a big deal because it showed a side of astronauts we don't often see, their human, vulnerable side. Space sickness, or what they call motion sickness in space, can be pretty rough. Imagine feeling dizzy, nauseous, and just all around terrible while you're trying to do your job millions of miles away from Earth. It's not fun. Aldrin dealing with this while on such an important mission just shows how tough and resilient astronauts have to be. But why is this important? Well, it reminds us that astronauts are people too. They face challenges and have to overcome them just like the rest of us. Aldrin sharing his story of space sickness helps us understand and appreciate the real human side of space exploration. It's not always smooth sailing or smooth flying in this case. Theories on extraterrestrial life and moon's far side. Now let's talk about something that's really out of this world. Buzz Aldrin has dropped some hints that have got everyone talking. He suggested that there might be hidden structures or even bases on the far side of the moon. This could mean something huge, like ancient civilizations or extraterrestrial activity. This idea isn't just some sci-fi fantasy. It's coming from a man who's actually walked on the moon. So when Aldrin talks about these possibilities, people listen. His comments have sparked a ton of interest and loads of speculation, not just among space enthusiasts, but even in the scientific community. Now think about it. The far side of the moon is this mysterious place that we've never seen from Earth. So when someone like Aldrin hints at something hidden over there, it's no wonder everyone's imagination goes into hyperdrive. Could there be structures we've never seen before? Signs of ancient moon visitors? Maybe even evidence of aliens? These ideas have sent people rushing to look at lunar images and data, searching for any clues that might support Aldrin's suggestions. But here's the thing. While some people claim they found evidence of weird structures or unnatural formations on the moon, a lot of it could be our brains playing tricks on us, seeing patterns that aren't really there. That said, the fact that a seasoned astronaut like Aldrin even entertains these ideas adds a serious dose of intrigue to the whole discussion. Observation of a mysterious object in space. During the historic Apollo 11 mission, Aldrin reported something extraordinary. He observed an object in space that he couldn't identify. This wasn't just a piece of their spacecraft or some random space junk. It was something different, something that even a seasoned astronaut like Aldrin couldn't recognize. Now, imagine this. You're thousands of miles away from Earth in the vast emptiness of space, and you see something mysterious floating out there. That's exactly what happened to Aldrin. This wasn't a quick glimpse either. He saw an object that seemed to move in a controlled way, not just tumbling through space like debris. This sighting was unusual enough to catch the attention of the entire crew. This sighting sparked a lot of conversations and theories, especially about the possibility of extraterrestrial life. It's one of those incidents that make you wonder what's really out there. Was it an optical illusion, a reflection, or something more? Some space enthusiasts even dared to ask if it could be evidence of intelligent life, taking an interest in humanity's first journey to the moon. Aldrin has been open about this experience, discussing it in interviews and being transparent about what he saw and felt. He didn't jump to any wild conclusions, but he also didn't dismiss what he saw as nothing. This account from Apollo 11 adds a layer of mystery and excitement to the mission's story. Belief in extraterrestrial life. Aldrin has some other fascinating thoughts about life beyond Earth. Think about it. The universe is incredibly huge, with billions of galaxies, each filled with billions of stars. Around those stars orbit countless planets. Aldrin thinks that in all that immense space, it's almost more unlikely that Earth is the only place with life. He's not just dreaming big. He's basing his ideas on the probabilities given the size of the cosmos. But Aldrin doesn't stop at just believing there's life out there. He's a big advocate for continuing to explore space, to push further into the unknown. Why? Because he thinks that by exploring, we might actually find other life forms. Imagine the breakthroughs and the leaps in understanding we could achieve if we encountered life beyond Earth. Aldrin's perspective is really a call to action for humanity. He's urging us to keep exploring space, not just to satisfy our curiosity, but also to connect with potential life out there. This isn't just about launching rockets and satellites. It's about a deeper understanding of our place in the universe. Life on the moon, possibilities and challenges. Now, when we think of the moon, we usually picture this barren, desolate landscape with extreme conditions. It's a place with no atmosphere, extreme temperature swings, and bombarded by cosmic rays and solar winds. Not exactly the kind of spot you'd think life would call home, right? But there's more to this story. It's this wild idea that life can actually hitch a ride across the cosmos, potentially even reaching the moon. This could happen through asteroids, comets, or even interstellar dust. Imagine tiny life forms or organic materials getting a lift from Earth or other planets and ending up on the moon. But that's not the only way life could make it to the moon. Human activity could also play a part. We've been sending spacecraft and landers to the moon since the 1950s. Now, what if some of these missions accidentally carried microscopic stowaways? It's entirely possible. In 2019, an Israeli spacecraft called Bereshit crashed on the moon. But it wasn't alone. It had a payload that included thousands of tardigrades. If you don't know what tardigrades are, they're these tiny, tough animals that can survive extreme conditions. We're talking about surviving in space. So there's a chance these little guys could be living it up on the moon right now. Now, we're not saying there's a thriving ecosystem up there. If there's any life on the moon, it's probably super simple, like bacteria or fungi. And it would have to be in very isolated spots, like inside rocks or in ice at the poles. While it's unlikely that the moon has its own native life forms, the idea that life could hitch a ride that isn't so far-fetched. It's these kinds of possibilities that make space exploration so exciting. We're constantly learning and re-evaluating our understanding of life in the cosmos. What do you think? Do you believe in Buzz Aldrin's observations? Could it possibly be any life beyond our planet, or even on our neighbor the moon? Let us know your thoughts in the comments below. We hope you found these facts intriguing. If you heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery.
We are looking for signs of life.
We have ignition and we have liftoff.
In the vast, silent expanse of space, a lone explorer travels further than any other human-made object in history. Launched in 1977, with a mission that was supposed to last just 5 years, Voyager 1 has defied all expectations, pushing the boundaries of human achievement and curiosity. For over 4 decades, it has been our silent ambassador to the cosmos, carrying messages from Earth to the unknown. But recently, something unexpected happened. This pioneer of space, now billions of kilometers from home, started sending back signals that have puzzled the brightest minds at NASA. What are these strange signals? Are we on the verge of a new discovery, or is Voyager 1 revealing the limits of our reach? Stay tuned as we dive into the mystery of Voyager 1's latest messages from the edge of space. What will we learn from this distant traveler? And how much longer can we keep the conversation going before silence takes over?
The sun will have a fate such as this, where at the end its outer layers of gas will escape into space.
The summer of 1977. In the summer of 1977, an opportunity arose that comes once in a lifetime, or more accurately, once every 176 years. This was the year NASA embarked on one of its most ambitious missions, the Voyager program. It began with the launch of Voyager 2 on August 20th, a date that would mark the beginning of humanity's grand tour of the outer solar system. But the story doesn't start there. It was a culmination of years of planning, all leading up to a narrow window when the outer planets aligned just right. This alignment allowed a spacecraft to hop from one planet to the next, using minimal fuel, in what's known as a gravity assist or slingshot maneuver. It was an ingenious solution to an otherwise insurmountable distance problem. Just a few weeks after Voyager 2's departure, its twin, Voyager 1, followed suit. Though launched second, Voyager 1 was destined to travel faster and farther, thanks to its unique trajectory. Both spacecraft, nearly identical twins, were engineered to withstand the harsh conditions of space and equipped with instruments designed to study the planets they would encounter. Weighing about as much as a small car, these probes were the epitome of human ingenuity and the embodiment of our desire to explore. The significance of their launch timing cannot be overstated. This fortuitous alignment allowed Voyager 1 and 2 to embark on a path that would see them visit Jupiter, Saturn, and for Voyager 2, Uranus and Neptune, providing humanity with its first close-up views of these distant giants. This grand tour, made possible by the planetary alignment and the gravitational slingshot effect, would forever change our understanding of the outer solar system. It was a bold plan, one that would leverage every ounce of momentum and every bit of data the Voyagers could muster as they set out to the stars, carrying the sights and sounds of Earth on their golden records. hoping to share a bit of our world with whatever or whoever might find them. The early discoveries. As Voyager 1 hurtled through the cold void of space, it approached the gas giant Jupiter in 1978, marking the beginning of a series of groundbreaking discoveries that would forever change our understanding of the outer solar system. With its cameras trained on this behemoth of swirling gases, Voyager 1 embarked on an extensive study, capturing detailed images that unveil the intricate beauty and complex dynamics of Jupiter and its moons. It was during this close encounter that Voyager 1 made one of its first major discoveries, the faint, dusty rings of Jupiter, a feature previously unknown to scientists. These ghostly rings challenged our perceptions and showcased the diversity of planetary ring systems. But the surprises didn't stop there. Voyager 1's journey brought it closer to Jupiter's moons, revealing 2 previously unseen moons, adding new members to Jupiter's already impressive family. Each of these discoveries provided insights into the formation and evolution of the solar system's planets and their satellites, opening new avenues for research and speculation. The spacecraft's adventure continued as it set its sights on Saturn, the jewel of the solar system, with its magnificent rings and numerous moons. However, to get the best possible view and scientific data, Voyager 1's trajectory needed a critical adjustment. This maneuver was not just a testament to the precision and ingenuity of NASA's engineers, but also a necessary step to avoid a potentially mission-ending collision with Titan, Saturn's largest moon. As Voyager 1 completed its flyby of Saturn, it discovered 4 new moons, further expanding our knowledge of the Saturnian system. The spacecraft also sent back detailed images of Saturn's rings, providing an unprecedented look at their structure and composition. Interstellar mission commencement in 1990. In 1990, a remarkable shift occurred for Voyager 1, transitioning from a trailblazer of our solar system to an envoy to the stars. After its groundbreaking explorations of Jupiter and Saturn, this intrepid spacecraft embarked on a journey that would take it to the very edge of our solar system and beyond, into the vast, uncharted territories of interstellar space. This phase of its mission marked not just a continuation of its voyage, but a leap into the unknown, a testament to human curiosity and our insatiable hunger for knowledge. One of Voyager 1's most awe-inspiring contributions during this time was the capture of the family photo of our solar system. Positioned about 6 billion kilometers away from the Sun, it turned its camera one last time to take a series of images that would encapsulate the entirety of our home system in a single poignant frame. This mosaic of the planets, seen as mere dots of light against the vastness of space, offered a humbling perspective on our place in the universe, famously inspiring Carl Sagan to reflect on the pale blue dot that is Earth. Understanding the need to preserve its limited resources for the long journey ahead, NASA made the decision to turn off Voyager 1's cameras after this monumental task. This was a calculated sacrifice, trading the ability to visually document its journey for the chance to extend its life and continue sending back valuable data. This pivotal moment underscored the shift in Voyager 1's mission from observation to endurance, as it powered down its eyes and ventured into the darkness, guided by the hope of discovering the secrets of interstellar space. As Voyager 1 pressed forward, it continued to communicate with Earth, its signals traversing the vast distance to bring insights back to those of us waiting eagerly for any news from the frontier. The spacecraft, now a silent witness to the cosmos, continues to traverse the boundary of the heliosphere, the protective bubble that marks the edge of the Sun's influence. In doing so, Voyager 1 has not only expanded our understanding of the solar system, but has also begun to peel back the layers of the interstellar medium, offering glimpses into the composition and dynamics of the space between the stars. Exiting the solar system. By 2012, this intrepid explorer had done the unthinkable. It had officially exited the solar system, venturing into the mysterious realm of interstellar space. This monumental achievement wasn't just a milestone for the spacecraft, but a historic event for humanity, marking the first time a human-made object had ever left the solar system. The announcement made by NASA in 2013 sent waves of excitement and wonder through the scientific community and the world. Voyager 1's transition into interstellar space was not just a testament to human ingenuity and the thirst for exploration. It symbolized the breaking of celestial boundaries. Imagine, a spacecraft designed with technology from the 1970s had now become humanity's most distant messenger, floating in the vastness of space far beyond the influence of our Sun. This was no small feat. Crossing into interstellar space meant that Voyager 1 had moved beyond the heliopause, the boundary where the solar wind from the sun is stopped by the interstellar medium, marking the edge of our solar system's influence. Voyager 1's journey into this unknown territory provides scientists with invaluable data about what lies beyond the protective bubble of our sun's wind and magnetic field. But what does it mean to exit the solar system? It means that Voyager 1 is now in a place where the sun's warmth and light do not reach, where the dynamics of space are governed not by our solar system, but by the galaxy itself. It's in a region where no spacecraft has ever ventured, sending back data from a place more remote than we had previously been able to explore. Every bit of information it sends us from this uncharted territory helps us understand more about the nature of the universe, continued communication and data transmission. Despite being engineered with a lifespan of only 5 years, Voyager 1 has shattered all expectations, continuing to serve as a vital link between the cosmos and Earth for over 4 decades. This achievement isn't just a testament to the spacecraft's design, but a beacon of human ingenuity and our unquenchable thirst for knowledge. Since its launch in 1977, Voyager 1 has been our eyes and ears, transmitting data across the unfathomable distance of interstellar space. As it ventured past giant gas planets and their mysterious moons, Voyager 1 relayed back to Earth stunning images and invaluable scientific data, reshaping our understanding of the solar system. Its journey has provided us with the first ever family portrait of our planetary neighborhood, a visual testament to our place in the universe. But Voyager 1's mission extends beyond mere observation. Embedded within its structure is the Golden Record, a time capsule intended for any potential extraterrestrial intelligence that might encounter the spacecraft. This record carries the sounds, images, and messages of Earth, a hopeful gesture of communication across the stars, strange signals, and current status. In the latest chapter of Voyager 1's epic saga, an enigma has emerged from the void. This season Voyager has begun beaming back a series of strange, indecipherable signals, igniting a whirlwind of speculation and intrigue among the scientific community. These anomalous transmissions, unlike anything the spacecraft has sent before, have left NASA's top scientists scratching their heads, wondering about the nature of these cryptic messages from the edge of interstellar space. Despite the spacecraft's advanced age having far surpassed its expected lifespan, the antenna of Voyager 1 remains in a state of remarkable health, faithfully maintaining its connection with Earth. This enduring link across the cosmic ocean allows Voyager 1 to still receive and execute commands sent from its terrestrial handlers, a small but significant reassurance amidst the growing mystery. As these puzzling signals continue to arrive, NASA is doubling down on its efforts to decipher them. Are they simply the result of an unknown glitch in the spacecraft's aging systems? Or could they be indicative of something more profound that Voyager 1 is experiencing in the uncharted territories of interstellar space? The implications are vast and varied, sparking intense discussion and research within the scientific community. The intrigue of Voyager 1's situation is heightened by its historical mission, which has already reshaped our understanding of the outer planets and the very nature of space beyond our solar system. Now, as it sends back these strange signals, it beckons us to look beyond our current understanding, challenging us to think differently about the universe and our place within it. The Golden Record. Amidst the cosmic silence, Voyager 1 carries with it a message from Earth, encapsulated within a gold-plated disc known as the Golden Record. This disc is not just a message. It's a time capsule, an interstellar greeting card designed to communicate the story of our world to extraterrestrial beings. Imagine a record player floating through space, carrying the very essence of humanity on its grooves. Crafted with meticulous care, the Golden Record holds over 35 sounds from Earth. These are not just random noises, but a carefully curated selection intended to depict life on our planet. From the haunting calls of humpback whales to the exhilarating sounds of a train passing by, each sound is a thread in the rich tapestry of life on Earth. But the Golden Record holds more than just sounds. It's also a visual archive containing 116 images of daily life on Earth. These images are a testament to our diversity and unity, showcasing the vastness of our landscapes, the complexity of our societies, and the simplicity of human moments. They depict who we are, what we look like, and how we live, work, and play. And then there's the music. Over an hour of Western pop music, alongside traditional music from various cultures around the world, forms a sonic bridge across the cosmos. This eclectic mix is a celebration of our artistic diversity, reaching out across the void in the universal language of melody and rhythm. Perhaps most poignant are the greeting messages from numerous former US presidents, translated into 55 different languages. This polyphony of human voices, extending a hand of friendship into the unknown, reflects our innate desire to connect, communicate, and understand. Challenges and the future of Voyager 1. As Voyager 1 continues its unparalleled journey through the cosmos, it faces an inevitable reality that challenges the very essence of long-distance space exploration. As it ventures further into the void beyond the sun's influence and into the cold expanse of interstellar space, the signals that once briskly traveled between Earth and the spacecraft now take longer, with messages averaging a 2-day journey each way. This increasing delay marks not just the physical distance, but also a growing gap in our ability to maintain a lifeline to humanity's most distant ambassador. This challenge isn't just about time, it's about the fragility of connection in the vastness of space. The further Voyager 1 gets, the more attenuated and precarious this connection becomes. There's a haunting realization that comes with this. Should something go wrong, there's no backup plan, no mission to repair or rescue Voyager 1. It's out there on its own, carrying on its mission in the silent vastness, reliant on systems designed decades ago. NASA, while hopeful, is pragmatic about the situation. The agency is pushing the limits of its ingenuity to keep the conversation going with Voyager 1, knowing all too well that each message received is a victory against the odds. The spacecraft's enduring silence could commence at any moment, not necessarily with a dramatic conclusion, but perhaps with a simple cessation of signals, leaving us to wonder about the fate of our most distant Voyager. This precarious situation underscores a broader theme in space exploration: the balance between the drive to explore further and the limitations of our technology. Voyager 1's journey is a testament to human ingenuity and a desire to explore the unknown. Yet it also serves as a reminder of the vastness of space and the limitations we face in our quest to understand it. As we continue to listen for Voyager 1's whispers from the depths of space, we stand on the brink of potential silence, a poignant reminder of the spacecraft's lonely journey and the vast, unexplored cosmos that lies beyond our reach. What do you think about this? We hope you found these facts intriguing. If you've heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery. While you're still here, feel free to click on other videos you will see on the screen right now.
Lurking in the night sky, just 700 light-years away, is a ticking time bomb that could detonate at any moment. Betelgeuse, a red supergiant star on the verge of a cataclysmic explosion, holds the power to light up our skies like never before. But when will this cosmic spectacle occur? The answer remains shrouded in uncertainty, leaving us to ponder the fate of this enigmatic star and its potential impact on Earth. In the midst of this cosmic mystery, one thing is certain: when Betelgeuse goes supernova, it will be a sight to behold. For 14 days, the night sky will be illuminated by a brilliant beacon nearly as bright as a full moon, a testament to the immense power unleashed in a stellar explosion. Yet, as we stand in awe of this potential celestial fireworks display, we are also confronted with a stark reminder of our own vulnerability in the face of cosmic forces beyond our control. A giant among stars, introducing Betelgeuse. In the vast expanse of the universe, Betelgeuse stands out as a true giant among stars. This colossal celestial body, known as a red supergiant, is one of the largest and most luminous stars ever discovered. With a mass estimated to be around 15 times that of our Sun, Betelgeuse is a behemoth that commands attention and ignites the imagination. To put Betelgeuse's size into perspective, if it were to replace our Sun at the center of the solar system, its outer atmosphere would extend beyond the orbit of Jupiter, engulfing the inner planets in a fiery embrace. This enormous size is a hallmark of red supergiants, which are stars nearing the end of their lives and have swelled to gargantuan proportions. Despite its immense size, Betelgeuse is a relatively young star in cosmic terms, with an age estimated to be less than 10 million years. This may seem like an eternity from a human perspective, but in the grand scheme of the universe, it is a mere blink of an eye. Betelgeuse's youth and massive size are intertwined, as more massive stars burn through their nuclear fuel at a much faster rate than smaller stars like our Sun. Betelgeuse's significance extends beyond its physical attributes. It is a star that has captured the attention of astronomers and the public alike due to its prominent position in the night sky. Located in the constellation of Orion, Betelgeuse forms the distinctive shoulder of the mythical hunter figure. Its reddish hue and fluctuating brightness make it easily distinguishable, even to the naked eye. For centuries, stargazers have marveled at Betelgeuse's presence in the heavens. It is the 10th brightest star in the night sky, a testament to its luminosity and relative proximity to Earth. At a distance of approximately 700 light-years, Betelgeuse is considered a neighboring star in the grand scale of the Milky Way galaxy. The fascination with Betelgeuse has only intensified in recent years, as astronomers have observed signs that the star may be nearing the end of its life. Fluctuations in brightness and changes in its shape have led scientists to speculate that Betelgeuse could be on the verge of a cataclysmic event, a supernova explosion. The prospect of witnessing a nearby supernova has ignited the imagination of both the scientific community and the general public. The last supernova observed in our galaxy occurred over 400 years ago, making the potential eruption of Betelgeuse a once-in-a-lifetime opportunity. However, the exact timing of when this cosmic spectacle will occur remains a mystery, as the complex internal dynamics of a star on the brink of destruction are still not fully understood. As we ponder the fate of Betelgeuse and await its inevitable demise, we are reminded of the cyclical nature of the universe. Stars, like all things, are born, live, and die, and their deaths can give rise to new cosmic wonders. The elements forged in the intense heat and pressure of a supernova become the building blocks for future stars, planets, and even life itself. While the supernova explosion of Betelgeuse is a source of fascination and anticipation, it also serves as a humbling reminder of our place in the cosmos. The forces that govern the life and death of stars operate on scales that dwarf human existence, both in terms of time and space. Yet, through the power of scientific observation and the enduring human spirit of curiosity, we can bear witness to these awe-inspiring events and marvel at the grand tapestry of the universe. As we delve deeper into the nature of Betelgeuse and its impending demise, we must first understand the fundamental processes that drive a star to the brink of destruction. What causes a massive star like Betelgeuse to meet its end in a spectacular supernova explosion? The answer lies in the complex interplay of nuclear fusion and the life cycle of these cosmic giants. The anatomy of a supernova. How stars explode. At the heart of a star's existence lies a delicate balance between the inward pull of gravity and the outward pressure generated by nuclear fusion. This cosmic tug-of-war ultimately determines the fate of a star, and in the case of massive stars like Betelgeuse, it sets the stage for a spectacular finale, a supernova explosion. Stars spend the majority of their lives fusing hydrogen into helium within their cores. However, as a star like Betelgeuse exhausts its hydrogen supply, the core begins to contract under its own immense gravity. This contraction heats the core to even higher temperatures, allowing the fusion of heavier elements to commence. In a cosmic dance of elemental alchemy, the star progresses through a sequence of fusion reactions, each one shorter in duration than the last. Helium fuses into carbon over 1 million years. Carbon fuses into neon in about 1,000 years. Neon fuses into silicon in a single year. And finally, silicon fuses into iron in a mere day. This rapid progression is a testament to the increasing instability within the star's core. The formation of an iron core marks a critical turning point in the star's life. Unlike the fusion of lighter elements, which release energy and support the star against gravity, iron fusion consumes energy. Once the core starts to fuse iron, it's basically stealing its own energy. This marks the beginning of the end for the star. As the iron core grows, it reaches a tipping point where it can no longer support its own mass. In a fraction of a second, the core collapses in on itself, triggering a cataclysmic chain of events. The outer layers of the star, once held aloft by the energy generated in the core, now rush inward at a staggering quarter of the speed of light. The exact details of how this rapid collapse and inward rush of matter trigger the explosive release of energy in a supernova remain one of the most perplexing mysteries in astrophysics. Scientists continue to grapple with the complex physics governing the interior of a dying star. What is certain, however, is the immense scale and power of a supernova. In a cosmic paradox, the death of a star like Betelgeuse gives rise to one of the most spectacular displays in the universe. For a brief moment, a single star can outshine an entire galaxy, its brilliance a stark reminder of the cyclical nature of the cosmos. As we stand in awe of the impending fate of Betelgeuse, we are left to ponder the signs and indicators that this colossal star is nearing its end. What clues might we glean from observing Betelgeuse in its final stages, and how can scientists unravel the enigma of predicting the precise moment of its cataclysmic demise? Signs of the end, predicting Betelgeuse's supernova. As we ponder the enigmatic nature of Betelgeuse and its impending supernova, astronomers have been vigilantly observing the star for signs that might indicate its approaching demise. In recent years, scientists have noticed several intriguing changes in Betelgeuse's behavior that have fueled speculation about the proximity of its explosive finale. One of the most striking observations has been the fluctuations in Betelgeuse's brightness. This variable luminosity is not uncommon among red supergiants, but the magnitude and frequency of these changes in Betelgeuse have raised eyebrows within the astronomical community. These fluctuations suggest that the star is undergoing significant internal changes, potentially related to the complex processes that precede a supernova. Another tantalizing clue has been the detection of unusual shape changes in Betelgeuse. Through high-resolution imaging techniques, astronomers have observed asymmetries and irregularities in the star's normally spherical shape. These deviations from a perfect sphere could be indicative of the tumultuous internal dynamics of a star on the brink of collapse. However, despite these intriguing observations, predicting the precise timing of Betelgeuse's supernova remains a formidable challenge. The internal workings of a massive star in its final stages are incredibly complex, involving a delicate interplay of nuclear fusion, gravitational forces, and energy transport. The exact tipping point at which a star's core collapses, triggering a supernova, is still not fully understood. Moreover, the timescales involved in stellar evolution are often measured in thousands or millions of years, making it difficult to pinpoint the exact moment of a star's demise. While the signs we observe in Betelgeuse are certainly suggestive of its impending fate, they do not provide a definitive timeline for when the supernova will occur. Scientists must also grapple with the limitations of our observational capabilities. Even with the most advanced telescopes and instruments, we can only glimpse the surface and outer layers of a star. The intricate processes occurring deep within the core, where the seeds of a supernova are sown, remain hidden from direct observation. To unravel the mysteries of Betelgeuse's impending supernova, astronomers must rely on theoretical models and computer simulations. By inputting the observational data and our current understanding of stellar physics, these models attempt to simulate the internal dynamics of a massive star in its final stages. However, the complexity of these systems means that even the most sophisticated models are approximations, subject to uncertainties and assumptions. Despite these challenges, the astronomical community remains captivated by the prospect of witnessing a nearby supernova in our lifetimes. The explosion of Betelgeuse would provide an unprecedented opportunity to study the mechanics of these cosmic events up close, offering invaluable insights into the life and death of stars. As we await the inevitable end of Betelgeuse, we are reminded that the universe operates on timescales that dwarf human existence. The anticipation and uncertainty surrounding this cosmic event serve as a poignant reflection of our place in the grand tapestry of the cosmos. Whether Betelgeuse meets its fate tomorrow or thousands of years from now, its story is a testament to the enduring mysteries and wonders that continue to captivate our imaginations. As we contemplate the eventual supernova of Betelgeuse, one question that inevitably arises is the potential impact of such a cataclysmic event on our own planet. Just how close is Betelgeuse to Earth? And could its explosive demise pose any danger to life as we know it? Betelgeuse and Earth, how close are we? As we contemplate the eventual supernova of Betelgeuse, one question that inevitably arises is the potential impact of such a cataclysmic event on our own planet. Just how close is Betelgeuse to Earth, and could its explosive demise pose any danger to life as we know it? Betelgeuse, the bright red supergiant star that has captured the imagination of astronomers and stargazers alike, resides approximately 642.5 light-years away from our celestial home. In the grand scheme of the cosmos, this distance might seem relatively close, especially when considering the vast expanse of the Milky Way galaxy. However, the gulf between Earth and Betelgeuse is still immense, spanning trillions upon trillions of kilometers. It is this considerable distance that serves as a cosmic shield, protecting our planet from the most destructive effects of Betelgeuse's eventual supernova. When the star finally exhausts its nuclear fuel and undergoes a cataclysmic collapse, the resulting explosion will unleash an unimaginable amount of energy, but the vast majority of this energy will dissipate long before it reaches Earth. One of the most common misconceptions surrounding Betelgeuse's supernova is the idea that it could spell doom for our planet, perhaps even triggering an apocalyptic scenario. However, the reality is far less sensational. At a distance of over 600 light-years, the harmful effects of the supernova, such as high-energy radiation and cosmic rays, will be significantly diluted by the time they traverse the cosmic expanse and reach Earth. As Dr. Sten Odenwald, an astronomer and author, explains, at these distances of hundreds of light-years, a supernova would have to be brighter than 100 million suns for 1 second to cause mass extinctions. Betelgeuse, while undoubtedly a massive and luminous star, falls well short of this threshold. This is not to say that Betelgeuse's supernova will go unnoticed on Earth. When the star does explode, it will briefly become one of the brightest objects in our night sky, rivaling the moon in its intensity. This cosmic spectacle will be visible even during daylight hours, a testament to the sheer power of a supernova. However, this dazzling display will be a harmless light show, not a harbinger of destruction. It is worth noting that the light from Betelgeuse's supernova will take approximately 642.5 years to reach Earth, given the star's distance. This means that if the star had already exploded, we would be witnessing its brilliant aftermath now, or in the near future. The fact that Betelgeuse still graces our night sky suggests that the supernova has not yet occurred, at least from our earthly perspective. While Betelgeuse's eventual supernova will undoubtedly be a source of fascination and scientific intrigue, it is crucial to dispel the myths and misconceptions surrounding its potential impact on Earth. The vast distance between our planet and this enigmatic star serves as a cosmic buffer, ensuring that life on Earth will continue unabated, even in the face of such a monumental stellar event. Yet, as we gaze up at the twinkling red supergiant, it is impossible not to wonder, what if Betelgeuse were to defy the odds and explode tomorrow? How would our world react to a cosmic event of such magnitude unfolding in real time? The thought is both thrilling and unnerving, a stark reminder of the unpredictable nature of the universe we call home. What if it happens tomorrow? Impact on Earth. As we ponder the possibility of Betelgeuse's supernova occurring in the near future, it's natural to wonder about the potential consequences for Earth. What if, by some twist of cosmic fate, the star were to explode tomorrow? While the chances of such an event happening are exceedingly slim, given the unpredictable nature of the universe, it's a scenario that captures the imagination and sparks curiosity. If Betelgeuse were to go supernova tomorrow, the immediate impact on Earth would be a dazzling display of cosmic fireworks. The star's explosive demise would briefly outshine the moon, becoming a beacon of light visible even during the day. This awe-inspiring spectacle would serve as a stark reminder of the immense power and beauty of the universe, captivating people across the globe. However, despite the visual grandeur of the event, the actual effects on Earth's atmosphere, technology, and life would be far less dramatic than the apocalyptic scenarios often depicted in popular media. At a distance of over 600 light-years, the harmful radiation and cosmic rays released by the supernova would be significantly diluted by the time they reached our planet, posing minimal risk to life on Earth. That's not to say that a nearby supernova like Betelgeuse's would have no impact on our world. The intense burst of light and energy could potentially disrupt satellite communications and cause minor fluctuations in Earth's magnetic field. However, these effects would be temporary and unlikely to cause widespread damage or chaos. In the midst of the excitement and speculation surrounding Betelgeuse's potential supernova, it's important to distinguish between scientific fact and sensationalized fiction. While the idea of a cosmic catastrophe unfolding before our eyes is undeniably thrilling, the reality is that Earth is well protected by the vast expanse of space separating us from the star. Nevertheless, the possibility of witnessing a nearby supernova in our lifetimes remains a source of fascination for scientists and the public alike. The opportunity to study such an event up close would provide invaluable insights into the life and death of stars, deepening our understanding of the universe we inhabit. As we await the eventual fate of Betelgeuse, whether it occurs tomorrow or thousands of years from now, we are reminded of the enduring mysteries that continue to captivate our imaginations. The story of this enigmatic star is a testament to the wonders and complexities of the cosmos, inviting us to ponder our place in the grand tapestry of existence. Yet, even as we speculate about the potential impact of Betelgeuse's supernova on Earth, we must acknowledge that our understanding of these cosmic events is far from complete. The science behind supernova, especially those involving massive stars like Betelgeuse, is a realm where fact and fiction often intertwine, leaving us with as many questions as answers. A mystery for the ages, science and speculation. As we delve into the mysteries that shroud the explosive demise of massive stars like Betelgeuse, we find ourselves at the intersection of scientific inquiry and boundless speculation. The study of supernovae has long been a source of fascination for astrophysicists, who strive to unravel the complex processes that govern these cosmic cataclysms. Yet, despite the wealth of knowledge accumulated over decades of research, the exact mechanisms that trigger a star's final, brilliant burst of energy remain a puzzle that continues to challenge our understanding. At the heart of this enigma lies the intricate interplay between the immense gravitational forces that seek to crush a star's core and the outward pressures generated by nuclear fusion reactions. As a star like Betelgeuse exhausts its fuel, a battle of cosmic proportions unfolds within its depths. The core, once a powerhouse of energy production, begins to falter, and the delicate balance that sustained the star for millions of years starts to unravel. It is in these final moments, as the core collapses under its own weight and the outer layers rush inward, that the seeds of the supernova are sown. However, the precise details of how this collapse ultimately triggers the explosive release of energy that we observe as a supernova remain shrouded in uncertainty. As noted by astrophysicists, the spectacular death blow can outshine all of the stars in the galaxy. But there's a problem. We still don't fully understand how a collapsing ball of iron and tons of falling gas create a giant fireball. This acknowledgement of the gaps in our knowledge serves as a testament to the complexity of the processes at work and the challenges that scientists face in their quest to unravel these mysteries. The study of supernovae is a realm where the boundaries between fact and fiction often blur, fueling the public's imagination and giving rise to a myriad of speculative scenarios. The idea of a nearby star, like Betelgeuse, exploding in a brilliant display of cosmic fireworks captures the attention of both scientists and laypeople alike, sparking discussions about the potential impact of such an event on our planet and our way of life. While the scientific community strives to separate the facts from the sensationalized narratives, the allure of the unknown and the potential for discovery continue to drive the exploration of these cosmic mysteries. In the midst of this interplay between science and speculation, the analogy of a cooking contest show emerges as a fitting metaphor for the frenzied nuclear reactions that precede a supernova. As the clock ticks down and the star's core begins to falter, the reactions become increasingly frantic, pushing the star towards its inevitable demise. This comparison serves to humanize the complex processes at work, making them more relatable and accessible to a broader audience. As we ponder the mysteries that still surround the explosive deaths of massive stars like Betelgeuse, we are reminded of the vast frontiers of knowledge that remain to be explored. Each new discovery, each piece of the puzzle that falls into place, brings us closer to a more complete understanding of the cosmos and our place within it. Yet, even as we make progress, we must acknowledge that the universe will always hold secrets that elude our grasp, ensuring that the study of supernova will remain a source of fascination and wonder for generations to come. The waiting game, our role in the cosmic theater. As we find ourselves in the midst of this cosmic waiting game, our role as observers and explorers of the universe comes into sharp focus. The story of Betelgeuse, with its uncertain fate and potential for a spectacular supernova, serves as a stark reminder of the wonders and mysteries that surround us. It is a testament to the power of scientific inquiry and the enduring fascination we have with the cosmos. While we may not know exactly when Betelgeuse will meet its explosive demise, the anticipation and excitement surrounding this event are palpable. As we wait and watch, we are invited to stay curious and engaged with the cosmic events unfolding before us. The study of stars like Betelgeuse opens up a realm of possibilities and questions that will continue to captivate scientists and the public alike. In the wake of this exploration, we find ourselves eager to delve deeper into the mysteries of the universe. The story of Betelgeuse is just one chapter in the grand cosmic narrative, and there are countless more waiting to be unraveled. As we look to the future, we can expect to encounter even more fascinating discoveries and puzzles that will challenge our understanding and ignite our imagination. So, as we ponder the fate of Betelgeuse and the profound impact it may have on our cosmic perspective, we invite you to join us on this journey of discovery. Stay tuned for more captivating content that will take you to the frontiers of astrophysics and beyond. In our next video, Just Now, James Webb Telescope just detected sudden 250% increase in Betelgeuse's brightness. We'll explore the latest developments in the Betelgeuse saga and what they could mean for our understanding of stellar evolution. The waiting game continues, but the rewards of our cosmic curiosity are sure to be extraordinary.
NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
The universe is a vast and awe-inspiring place, and although Earth is an incredible planet, it is just a tiny speck in the grand scheme of things. With the advancement of technology, humans have been able to launch rockets and satellites into space, leading to an insatiable thirst for knowledge about the mysteries of the universe. While we have a decent understanding of how the universe works, much of our information is based on conjecture and speculation. That's why space probes like Voyager 1 and Voyager 2 are so crucial to our comprehension of the cosmos. These probes are beaming back real-time data, shedding light on the farthest reaches of our solar system and interstellar space, which we may not be able to visit for many years to come. But what happens when this data includes a terrifying warning that changes everything we thought we knew about the universe? Join us as we delve into what Voyager has discovered so far and the unsettling message it has sent us about the future. For nearly half a century, the Voyager missions have been at the forefront of space exploration, providing invaluable insight into the mysteries of our solar system. It's hard to believe that these missions were not intended to last this long, given the wealth of information they have yielded. The story of how the Voyager program came to be is a fascinating one. It all began with a fortuitous discovery by Michael Minovich, who realized that a spacecraft could use the gravity of a planet to slingshot further into space. This led to the launch of Voyager 1 and Voyager 2 in 1977, with the aim of studying Jupiter and Saturn. What followed was nothing short of a miracle. Both Voyagers are equipped with 3.7-meter radio dishes and 16 thrusters to adjust their orientation and direct their dishes towards Earth. Their engines use hydrazine fuel, and their electronic components are powered by plutonium-fueled thermoelectric generators. Both carry 11 scientific instruments, half of which were designed to study planets and have since been turned off. The grand tour of the 4 planets has now become a remarkable achievement in human exploration. Voyager 2 successfully completed the first-ever close observations of Uranus in 1986 and Neptune in 1989, while Voyager 1 overtook Voyager 2 a few months after launch, passing Jupiter in 1979 and Saturn in 1980, and has become the farthest distant artificial object from Earth. While Voyager 2 still has 5 functioning instruments, Voyager 1 only has 4, but they both remain crucial for gathering valuable data on the deep reaches of space. Today, the 2 spacecraft continue to journey beyond the Sun's influence and into interstellar space, sending back valuable data on the cosmic environment. Before delving into the messages received from Voyager 1, let's first look into some of the discoveries and things both the Voyagers encountered along the way. Imagine embarking on an epic journey to explore the uncharted depths of our solar system with 2 trusty spacecrafts as your companions. Your first mission? Take a closer look at the mighty Jupiter and Saturn systems. And boy, did those probes deliver! They transmitted a plethora of never-before-seen images and gathered extensive data, completely revolutionizing our understanding of these gas giants and the iconic ringed planet. But while Voyager 1 bid adieu to our solar system and ventured into interstellar space, Voyager 2 still had some exciting pit stops in store. In 1981, a corrective maneuver was made to set Voyager 2 on a course towards Uranus, and after exceeding its originally predicted lifespan twice, the spacecraft finally arrived at the remote ice giant in January 1986. But that was just the beginning. On its way to Uranus, Voyager 2 discovered 10 previously unknown moons, adding to the growing celestial family. But the ultimate destination was Neptune, where Voyager 2 captured more than 9,000 images and made an incredible discovery: 9 previously unknown moons. But that wasn't all. Triton, the largest of Neptune's moons, had some fascinating secrets to reveal. It turns out that Triton's diameter was not as previously thought, and the satellite had surprisingly few impact points on its surface. And its brown-white coloration? Geysers. These volcanic formations spew out liquid nitrogen that freezes into white nitrogen snow upon landing on the surface. With these incredible discoveries, the Voyager mission left an indelible mark on our understanding of our cosmic neighborhood. No other spacecraft has revisited Uranus and Neptune after Voyager 2's journey. However, scientists have still been able to observe and study incredible phenomena on these planets from afar. And now, get ready to be amazed as we reveal the secrets of these mysterious spectacles. Uranus. When it comes to ice giants in our solar system, the list is pretty short, with only 2 members, Uranus and Neptune. Despite the name, the majority of these planets' material is not actually frozen, but instead consists of hot, supercritical fluids made up of volatile chemical compounds like water, ammonia, and methane. It's a state of matter that combines the properties of liquids and gases. At an average solar distance of 1.8 billion miles, Uranus is the second outermost planet in our solar system, and its diameter is over 4 times that of Earth. It takes Uranus about 84 years to orbit the Sun, and during that time it does something strange. It appears to be lying on its side. The reason for this peculiar axis inclination is unknown, but scientists think it may have collided with a large protoplanet early on. This could also explain the 27 moons orbiting Uranus, which may have formed from the debris of the collision. And if that's not enough to intrigue you, a massive white spot was discovered on Uranus's upper atmosphere about 10 years ago thanks to the Hubble Space Telescope. It turned out to be a gigantic storm whipping around at speeds of up to 89 miles per hour, larger than the United States. But if you think that's wild, imagine the freezing temperatures of Uranus's methane and ammonia clouds, which can drop to a chilling minus 323 degrees Fahrenheit. And don't forget, just like Saturn, Uranus has its own ring system, although it's much sparser and less abundant. Neptune. In 1846, a bluish shimmering planet was added to the star charts, and we named it Neptune. This outermost planet of our solar system is nearly 3 billion miles away from the Sun, making it quite the loner. To put that in perspective, the distance between Earth and the Sun is only about 90 million miles. Despite its distance, Neptune is similar in size to its ice giant neighbor Uranus, with a diameter of 31,000 miles. However, in terms of mass, Neptune takes the cake with a whopping 17 Earth masses compared to Uranus's 14.5 Earth masses. Neptune takes a whopping 165 years to orbit around the Sun, but it spins quite quickly on its axis, taking only 16 hours to complete one rotation. When NASA's Voyager 2 spacecraft visited Neptune in 1989, it captured some wild weather phenomena such as bright bands of clouds in the atmosphere and storms that reached top speeds of up to 1,305 miles per hour, the fastest winds observed on any celestial body. Experts believe that the lack of solar energy reaching Neptune allows these storms to whip up to such incredible speeds, but there is a chance they may disappear into thin air one day. During the Voyager 2 mission, scientists discovered the Great Dark Spot, a massive formation as large as Eurasia that was believed to be a hole in the planet's visible cloud cover. However, when scientists attempted to find the spot again a few years later, it was nowhere to be found. Some theories suggest that heat from Neptune's core caused turbulence in the atmosphere and tore the structure apart. Speaking of Neptune's core, despite the volatile nature of this planet, scientists believe it has a massive heart. The core is estimated to be 1 to 1.5 Earth masses and composed of metal and rock, with temperatures likely reaching nearly 13,000 degrees Fahrenheit and pressures estimated at several million bar. The magnetic fields of Uranus and Neptune have been a source of wonder for scientists for a long time. These invisible forces have a peculiar characteristic. They are tilted towards the rotation axis and deviate significantly from the planet's physical center. No one has yet unraveled the mystery behind these curious alignments. One thing that is certain is that Neptune's magnetic field is 27 times stronger than Earth's. On the other hand, Uranus's magnetic field is surprisingly weaker than our home planets. Experts believe that the magnetic fields of these gas giants are generated by movements in comparatively small depth, possibly caused by ionized water. But that's not the only secret that lies within these planets. It is widely believed that Uranus and Neptune have massive cores surrounded by dense layers consisting of hydrocarbons, ammonia, and water. Scientists have been intrigued by the incredible processes that might be happening under the immense pressures at the center of these planets. One fascinating theory suggests that diamonds are raining inside Uranus and Neptune. This idea, which was once merely a thought experiment, was actually proven by a group of researchers a few years ago. The team used polystyrene, a plastic made up of hydrogen and carbon atoms, to recreate the extreme pressure conditions inside the ice giants. They sent 2 shock waves through the substance to see whether the hydrocarbon compounds would split under such pressure. The experiment generated a pressure of 1.05 million bar and raised the thermometer to a scorching 9,000 degrees Fahrenheit. The result was an astonishing shower of glittering diamonds, as nearly all the carbon atoms joined together to form tiny diamond structures. The diamonds that form in Uranus and Neptune would be much larger than those simulated in the laboratory. After they are created, these cosmic gems sink gradually towards the planet's core over a period of thousands of years. The thought of diamond rain on other planets is truly mind-boggling and adds to the intrigue and fascination of these mysterious gas giants. Over the past decade, the 2 probes have ventured into a vast and mysterious region known as the interstellar medium, the space between stars filled with sparse material. And they're still uncovering new discoveries. One of the most surprising findings is the strength and direction of the interstellar magnetic field, which has sparked lively debates among experts about the shape and activity of the Sun's magnetic domain, the heliosphere. Previously thought to be shaped like a comet, the heliosphere may actually be more spherical. And what happens to the heliosphere when sunspots appear and disappear? The spacecraft has provided some intriguing clues. When the solar wind, a flow of charged particles emanating from the Sun, comes to a halt, it marks the beginning of the interstellar medium. This ionized gas or plasma is like a rock in a river, pushing against the cooler, denser plasma flowing around it. The sun-carved cavity that forms is called the heliosphere, with its edge called the heliopause, similar to how the top of Earth's troposphere is called the tropopause. Don Gannett, a University of Iowa researcher who worked on the Voyager mission, says that when the spacecraft launched, they had no idea how far the heliopause was. Some speculated it could be as close as Jupiter, which is only 5 times further from the Sun than Earth. But as Voyager ventured further, estimates of the heliopause's distance increased, ruling out Jupiter, Saturn, Uranus, and Neptune. No one knew when or where the spacecraft would enter interstellar space. According to Don Gurnett, shortly after Voyager passed by Neptune, it detected signs of the heliopause in the distance. The spacecraft picked up strong radio waves between 2 and 3 kilohertz in July of 1992, which were later attributed to 6 significant flares on the Sun that occurred over a year prior. The researchers found that the plasma from the flares eventually made its way to the heliopause, where it caused electrons to oscillate and release radio waves. The frequency of these radio waves implied a density matching that expected for the interstellar medium, revealing that the local interstellar medium is far denser than the outer heliosphere. Despite appearing like a pure vacuum on Earth, it is actually quite tenuous. By calculating the speed of outbound solar material and the time it took to hit the boundary, the distance of the heliopause from the Sun was revealed to be between 116 and 177 astronomical units, providing a fascinating insight into our solar system's outer boundaries. When Gurnett claimed that Voyager had detected radio waves at the heliopause, he was met with skepticism from many scholars. Not only were these radio waves unprecedented, but Gurnett's interpretation of them also suggested that the heliopause was located at a significant distance from the Sun. To put this into perspective, the distance between the Sun and Neptune is just 30 astronomical units, while the heliopause seemed to be much farther away. Despite these doubts, Voyager 1 successfully crossed the heliopause at a distance of 121.6 astronomical units, consistent with Gurnett's prediction. However, due to the controversy surrounding the claim, NASA decided to delay the announcement of the accomplishment for over a year, although Voyager 1 did observe some indications that it had left the heliosphere, such as a decrease in high-energy particles from the Sun and an increase in cosmic rays from beyond the solar system. Many researchers were still not convinced. One issue was that Voyager's plasma instrument had stopped functioning, making it impossible to measure the sudden increase in particle density that occurs when leaving the heliosphere. Additionally, it was expected that the magnetic field would point in a different direction beyond the heliosphere, but this did not happen. Even today, scientists are still scratching their heads trying to explain why the magnetic field outside the heliosphere aligns with the magnetic field inside. It's a mystery that has yet to be solved. Voyager's incredible journey was partly aided by the Sun's outbursts. In 2012, massive solar storms stirred the plasma Voyager 1 traveled through, causing electrons to emit radio waves. These waves indicated that Voyager had entered a denser region of space. On November 5, 2018, Voyager 2 also crossed the heliopause without raising concerns. Its plasma instrument recorded a significant spike in particle density and higher temperatures, likely due to plasma compression when entering the heliosphere. Like Voyager 1, Voyager 2 observed the disappearance of solar wind and an increase in cosmic rays, with an unchanged magnetic field. Stamatios Tom Crimiges of Johns Hopkins University noted that both spacecraft crossed at similar distances despite different solar cycles in 2012 and 2018. The heliosphere, influenced by the waxing and waning of sunspots over an 11-year cycle, expands and contracts. Despite lower solar wind pressure in 2012 than in 2018, the similar distances suggest the heliopause is more resilient than previously thought. Despite the exact form of the heliosphere remaining a mystery, Voyager 1 and Voyager 2 continue to sail away from it. By the end of this year, Voyager 1 will be 155 astronomical units from the Sun, with signals taking over 22 hours to reach us. Voyager 2 will be 129 astronomical units away and is set to pass Pioneer 10 in late 2023 to become the second furthest spacecraft ever. These spacecraft are now further apart from each other than from Earth. In May last year, Voyager 1's Attitude Articulation and Control System, AACS, began sending confusing data. Despite this, the spacecraft remained in good shape, with a strong, steady signal indicating the antenna was still pointed at Earth. The AACS continued to experience issues, but the science systems functioned normally. NASA identified the problem as the AACS transmitting telemetry via a long-defunct onboard computer. Engineers instructed the AACS to use the correct computer, solving the issue. The next step is to determine what caused the system to switch in the first place. Although not a serious concern for Voyager 1's safety, identifying and correcting the fundamental cause is necessary to prevent future anomalies. In the vast expanse of interstellar space, Voyager 1 has been a true pioneer, journeying beyond the protective shield of our Sun's magnetic field for over a decade. Despite the hostile environment with high-energy particles and cosmic radiation bombarding the craft, Voyager 1 has continued to push forward, delivering valuable data and insights about the mysteries of deep space. According to Susan Dodd, the project manager for Voyager 1 and 2, strange occurrences like the recent AACS malfunction are expected in this groundbreaking mission. After 45 years of exploration, the Voyagers remain a testament to human ingenuity and determination. Let's hear your thoughts about the Voyager mission in the comments section below.
For centuries, our gaze has been drawn upwards to the mysteries of the cosmos, pondering what lies beyond the glittering veil of stars. Today, the James Webb Space Telescope, JWST, stands at the helm of cosmic exploration, ushering us into a new era of discovery. This marvel of technology, equipped with the most advanced instruments, is poised to unravel the secrets of the universe. But what have these new eyes in the sky revealed? How might these groundbreaking discoveries reshape our understanding of the cosmos? Join us as we delve into the revelations of the James Webb Space Telescope and ponder the profound questions they raise about our place in the universe. The James Webb Space Telescope, often referred to simply as JWST, represents a significant leap forward in our ability to observe the cosmos. Launched in December 2021, this telescope is often hailed as the successor to the iconic Hubble Space Telescope. While Hubble has served us incredibly well, JWST is designed to surpass its predecessor with a suite of advanced technologies and instruments. Equipped with a large primary mirror that spans 6.5 meters across, considerably larger than Hubble's 2.4 meters, JWST can collect more light and observe objects in far greater detail. This larger size allows it to look deeper into space and further back in time, giving astronomers a clearer view of the early universe. One of JWST's most notable advancements is its ability to observe primarily in the infrared spectrum. This capability is crucial because it allows the telescope to see through cosmic dust clouds that obscure other wavelengths of light. By doing so, JWST can reveal hidden regions of space and provide new insights into the formation of stars, galaxies, and planetary systems. The mission objectives of JWST are broad, yet profoundly significant. They include unraveling the mysteries of our solar system, exploring distant worlds around other stars, and probing the mysterious structures and origins of our universe and our place within it. Each of these objectives not only sets the stage for a deeper understanding of the cosmos, but also ensures JWST's role as a cornerstone of astronomical research for the foreseeable future. Now let's dive into the concept of the observable universe and what that really means for us on Earth. The observable universe includes everything that we can see from our vantage point here on Earth, whether through the naked eye or with the most advanced telescopes like the James Webb Space Telescope. It's important to note that when we talk about the observable universe, we're really talking about the portion of the universe from which light has had enough time to reach us since the beginning of the cosmic timeline, the Big Bang, which happened about 13.8 billion years ago. This brings us to the mind-boggling scale of the observable universe. It measures about 93 billion light-years in diameter. Now, a light-year isn't a measure of time, but of distance. It represents the distance that light can travel in 1 year, which is approximately 5.88 trillion miles, or about 9.46 trillion kilometers. To put this in perspective, imagine light traveling at about 670 million mph, which is roughly the speed of light, and covering that enormous distance in a year. So when we say the observable universe is 93 billion light-years across, we're saying that it spans a distance of about 546.84 billion trillion miles, or 878.58 billion trillion kilometers. This immense scale helps us grasp just how vast the cosmos really is, filled with galaxies, stars, and other celestial phenomena, each of which could hold countless mysteries waiting to be uncovered. In the early 20th century, our understanding of the universe underwent a dramatic transformation thanks to Albert Einstein and Edwin Hubble. In 1915, Einstein introduced his theory of general relativity, which radically changed how we understand gravity. Unlike Newton's view of gravity as a force acting at a distance, Einstein described it as the effect of curvature of spacetime caused by mass and energy. This groundbreaking theory led to the realization that the universe isn't static but is, in fact, in motion. This theoretical framework set the stage for a pivotal observation by Edwin Hubble in 1929. Hubble discovered that galaxies are moving away from us, and crucially, the farther a galaxy is, the faster it appears to be receding. This phenomenon indicated that the universe is expanding, a concept that was initially counterintuitive even to Einstein. The tool central to understanding this expansion is the concept of redshift. Redshift occurs because as the universe expands, the light from distant galaxies is stretched along with the space through which it travels. This stretching shifts the light towards the red end of the spectrum, hence the name redshift. By measuring how much the light from a galaxy has been redshifted, astronomers can determine how fast it is moving away from us. This not only confirms the expansion of the universe, but also helps in estimating the rate of that expansion. Through these observations, redshift has become a fundamental aspect of cosmological research, allowing us to peer back into the universe's history and better understand its dynamic nature. As we gaze into the cosmos, one of the most intriguing questions we encounter is, what lies at the edge of the observable universe? The observable universe includes everything we can see from Earth, measuring out to about 93 billion light-years in diameter. But what exists beyond this boundary? Theories about the universe's edge often delve into complex and fascinating ideas about the nature of the cosmos itself. One popular theory suggests that the universe might be infinite. If this is true, it means there is no actual edge in the way we might traditionally imagine. Space could extend endlessly, containing an infinite number of galaxies and celestial phenomena, all interwoven in the fabric of the cosmos. Alternatively, some theorists propose that the universe is finite but without any edges or boundaries. This model suggests that space curves back on itself, much like the surface of a sphere. In this scenario, if you could travel far enough in one direction, you might eventually return to your starting point, traversing the universe much like circumnavigating the globe. This concept challenges our perceptions and highlights the extraordinary complexity and beauty of the universe. Both theories showcase human curiosity and our pursuit of understanding the universe's vast scale and form, providing a framework to explore the cosmos further with advanced technologies like the James Webb Space Telescope. The James Webb Space Telescope has once again turned our understanding of the cosmos on its head with its latest discoveries. Among the most startling revelations are the observations of 6 massive galaxies that existed surprisingly early in the universe's history, between 500 million and 700 million years after the Big Bang. Prior to these findings, scientists expected this era to contain only small, fledgling galaxies. The existence of such large galaxies so soon after the Big Bang poses a significant challenge to our existing models of galaxy formation. These galaxies, each comparable in mass to our 13-billion-year-old Milky Way, contain mature red stars, suggesting that they developed far more rapidly than any models had predicted. This rapid maturity contradicts previous assumptions that galaxies in the early universe started as small conglomerations of stars and dust, which gradually grew over billions of years. The James Webb Space Telescope, through its deep-field imaging capabilities, not only captured these galaxies, but provided data that has left astronomers reeling. These findings compel astronomers to revisit and possibly revise our understanding of cosmic history, particularly how galaxies and structures came into being so shortly after the universe's birth. This breakthrough demonstrates the JWST's unmatched capacity to expand our understanding of the early universe, adding depth to our knowledge of galaxy formation and challenging existing scientific theories. The James Webb Space Telescope, JWST, represents a significant leap forward in astronomical technology, equipped with state-of-the-art instruments designed to peer deeper into the cosmos than ever before. Among its most notable features is its suite of infrared capabilities, which allow it to observe the universe in wavelengths of light invisible to the human eye. This is crucial because infrared light can penetrate cosmic dust clouds that often obscure other forms of radiation. One of JWST's primary tools is its powerful infrared cameras. These cameras are essential for observing the early universe, as they capture images of celestial objects whose light has been stretched into the infrared spectrum by the expanding universe. This stretching, known as redshift, is more pronounced in objects that are farther away, meaning that JWST's infrared cameras can see further back in time than those of any previous telescope. In addition to its cameras, JWST is equipped with spectrographs that add another layer of observational power. Spectrographs are instruments that split incoming light into its component colors or wavelengths. This allows astronomers to analyze the properties of that light, including its composition, temperature, and motion. By studying the spectral lines in these light signatures, scientists can determine the chemical composition of distant stars and galaxies, uncovering details about their age, mass, and even potential for planets. Moreover, the telescope's use of coronagraphs, a technology designed to block out the blinding light of stars, enables the direct observation of nearby exoplanets and other faint objects around those stars. This combination of advanced instruments makes JWST uniquely capable of studying the formation and evolution of stars, galaxies, and planetary systems, providing a window into processes that occurred billions of years ago, only a few 100 million years after the Big Bang. In a recent groundbreaking discovery by the James Webb Space Telescope, astronomers have uncovered evidence of 6 massive galaxies that existed surprisingly early in the universe's history, between 500 million and 700 million years after the Big Bang. This revelation is particularly startling because prior to this, scientists had only expected to find small, nascent galaxies at such an early stage in cosmic history. The presence of these large, mature galaxies so soon after the Big Bang poses significant challenges to our existing theories of how galaxies form and evolve. Traditionally, astronomers believed that galaxies started small and gradually grew larger over billions of years through processes such as star formation and mergers with other galaxies. However, the discovery of these universe-breaker galaxies, as they have been aptly nicknamed, suggests that galaxy formation might occur more rapidly and differently than previously thought. Each of these galaxies appears to be as large and as mature as our own Milky Way, which is roughly 13 billion years old. This unexpected maturity of galaxies and what can be considered the cosmic dawn forces astronomers to reconsider the physics of early universe galaxy formation. It suggests that significant amounts of star formation must have happened very quickly to allow these galaxies to reach such a mature state so early on. These findings not only raise questions about the speed and process of galaxy formation, but also hint at the possibility that the conditions in the early universe might have been different from what the current models suggest. Now let's look at what the future holds. As we continue to push the boundaries of our cosmic knowledge, the future of space exploration looks brighter than ever, thanks to upcoming missions and advanced telescopes. A particularly exciting development is the planned launch of the Nancy Grace Roman Space Telescope, formerly known as the Wide Field Infrared Survey Telescope, or WFIRST. Scheduled for launch in 2027, this telescope will carry on the legacy of the James Webb Space Telescope by delving even deeper into the mysteries of the cosmos. The Roman Space Telescope is designed to explore various fundamental questions in the fields of dark energy, exoplanets, and infrared astrophysics. With a primary mirror diameter of 2.4 meters, identical to that of the Hubble Space Telescope, the Roman Space Telescope will offer a new perspective on the universe. Its wide-field instrument will allow it to capture images over a field of view more than 100 times larger than that of the Hubble, enabling it to survey the sky at unprecedented scales. This will not only increase our ability to observe the cosmos, but will also dramatically enhance our understanding of the universe's structure and evolution. Moreover, the Roman Space Telescope will be equipped with a coronagraph instrument, which is specifically designed for high-contrast imaging and spectroscopy of nearby exoplanets. This instrument will be crucial for blocking out the overwhelming glare of stars, allowing the telescope to directly image exoplanets. Such capabilities are expected to revolutionize our insights into planetary formation and offer new possibilities for studying potentially habitable planets. By building on the discoveries made by the JWST, the Roman Space Telescope will extend our cosmic reach, bringing us closer to answering some of the most profound questions about our universe. This seamless integration of past achievements with future potential underscores the dynamic and ever-evolving nature of astronomical exploration. In summary, the advent of the Nancy Grace Roman Space Telescope marks a significant milestone in our ongoing quest to understand the cosmos. By leveraging cutting-edge technology and building upon the foundation laid by the James Webb Space Telescope, this new mission promises to expand our horizons further, offering deeper insights into the universe's secrets and potentially uncovering new realms of knowledge in dark energy, exoplanets, and beyond. As we look to the future, the potential for discovery seems limitless, promising a new era of astronomical breakthroughs. We hope you found these facts intriguing. If you've heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery. While you're still here, feel free to click on other videos you will see on your screen right now.
The universe is teeming with planets outside our solar system, and each one offers a unique glimpse into the vast complexities of space. Enter the James Webb Space Telescope, JWST, a marvel of modern science and a beacon of hope for astronomers searching for Earth-like planets. The JWST, with its unparalleled ability to peer into the depths of space through infrared eyes, has transformed our quest to understand distant worlds. Today, we're diving deep into one of JWST's most thrilling revelations yet, the discovery of Gliese 163c. This exoplanet, located in the habitable zone of its star, presents conditions that might just support life as we know it. Gliese 163c is not just another celestial body, it represents a potential future, a new chapter in human exploration, and perhaps the answer to the age-old question, are we alone in the universe? The telescope, the James Webb Space Telescope, JWST, stands as a pinnacle of astronomical technology equipped with tools specifically designed to observe distant exoplanets with unprecedented clarity and depth. Among its suite of sophisticated instruments, the near-infrared camera, NIRCam, is pivotal. NIRCam not only captures detailed images of exoplanets, but also analyses their atmosphere by observing the light passing through it when a planet transits its star. This helps identify elements that might indicate habitable conditions or even the presence of life. Another groundbreaking instrument aboard the JWST is the Mid-Infrared Instrument, MIRI. MIRI extends the telescope's vision further into the infrared spectrum, which is crucial for studying cooler celestial objects. This capability is vital for examining the thermal characteristics of an exoplanet, providing insights into its surface temperature and conditions that are essential for assessing habitability. Equally important, the near-infrared spectrograph, NIR-SPEC, allows astronomers to dissect the chemical makeup of an exoplanet's atmosphere by spreading out the starlight into a spectrum. This tool can detect water vapor, methane, and other organic compounds, offering clues about the potential for life as we understand it. With these advanced tools, the James Webb Space Telescope not only seeks to find exoplanets, but also to explore them in a depth that was previously unimaginable, bringing us closer than ever to understanding whether planets like Gliese 163c could truly be called Earth's cousins. The discovery. The James Webb Space Telescope made headlines with its discovery of Gliese 163c, an exoplanet that quickly captured the attention of astronomers and space enthusiasts alike. This significant find was announced after JWST's detailed analysis of the star system Gliese 163, located about 49 light-years away in the constellation Dorado. Using its advanced near-infrared spectrograph, JWST was able to detect the chemical signatures and thermal properties that suggest Gliese 163c might be within the star's habitable zone. Initial observations of Gliese 163c indicated several exciting possibilities. The planet's orbit places it at just the right distance from its star to potentially allow liquid water to exist on its surface, an essential criterion for Earth-like life. Moreover, the spectral data revealed hints of an atmosphere, which is another critical factor in considering the habitability of a planet. These early findings have laid the groundwork for more detailed studies, making Gliese 163c a prime candidate in the search for life beyond Earth. Criteria for habitability. When scientists search for potentially habitable planets like Gliese 163cc, they primarily focus on three critical criteria: atmosphere, temperature, and the presence of water. Each of these elements plays a pivotal role in supporting life as we understand it. Firstly, an atmosphere is crucial because it can regulate temperature, protect biological entities from cosmic and solar radiation, and provide essential gases that biological processes might require. For instance, an atmosphere rich in oxygen and nitrogen, like Earth's, can support aerobic life forms and water cycles. Secondly, the temperature of a planet is equally significant. It must be neither too hot nor too cold, enabling the existence of liquid water on the planet's surface. This Goldilocks zone is where temperatures are just right for liquid water to exist, not so cold that it freezes solid, and not so hot that it vaporizes away. Finally, the presence of water is often considered a key marker for life. Water is a solvent in which biochemical reactions occur, crucial for life on Earth. Thus, finding signs of water on Gliese 163c, whether in vapor form in the atmosphere or as liquid on the surface, would be a strong indicator that the planet could potentially be hospitable to life forms. These criteria guide astronomers as they use the JWST to observe exoplanets across the galaxy, searching for those rare worlds where conditions might just be right for life to emerge. Characteristics of Gliese 163c. Gliese 163c stands out in the cosmic lineup of exoplanets due to its intriguing characteristics. It orbits its host star, Gliese 163, at a distance that places it squarely within the star's habitable zone, which is the region where conditions might be just right for liquid water to exist on the planet's surface, a crucial factor for life as we understand it. The planet is approximately 6.9 times the mass of Earth, classifying it as a super-Earth. This size suggests a rocky composition with a more substantial atmosphere than our home planet, which could lead to a greenhouse effect, potentially warming the planet. The orbit of Gliese 163c is particularly fascinating. It completes a full revolution around its star in approximately 26 Earth days. Such a short orbital period indicates that the planet is much closer to its star than Earth is to the Sun. However, because Gliese 163 is a red dwarf and much cooler than our Sun, this proximity places Gliese 163c in the sweet spot for temperate conditions. Comparatively, Earth orbits the Sun every 365 days, which reflects our moderate distance from a much hotter star. The environmental conditions on Gliese 163c, inferred from its orbit and size, suggest a world that could host thick atmospheric layers capable of trapping heat. If water exists, its state, whether vapor, liquid, or ice, would heavily depend on atmospheric composition and surface pressure. In contrast, Earth's well-balanced atmosphere and magnetic field have created a stable environment where water can exist in all three states, supporting a diverse range of life forms. As we continue to study Gliese 163c, understanding these key differences and similarities will help scientists better assess the planet's potential for habitability and life. Technology behind the discovery. The James Webb Space Telescope leverages cutting-edge technology to unveil the secrets of distant worlds like Gliese 163c. Central to its success are several key instruments, each playing a vital role in this cosmic detective work. The near-infrared camera, NIRCam, is JWST's primary imager, capturing high-resolution images that bring distant stars and their orbiting planets into clearer view than ever before. This capability is crucial for spotting minute changes in brightness and position that hint at the presence of exoplanets. Additionally, the mid-infrared instrument, MIRI, provides new insights into the thermal characteristics of Gliese 163c, allowing scientists to analyze the heat signatures that differentiate it from its stellar background. MIRI's sensitivity to longer wavelengths is ideal for studying cooler objects in space, making it indispensable for assessing the habitability of colder, Earth-like planets. Another essential tool is the near-infrared spectrograph, NIRSpec, which can disperse the light from Gliese 163c into its component wavelengths. This spectroscopic analysis helps astronomers determine the planet's atmospheric composition by identifying specific molecular signatures, such as water vapor, methane, or carbon dioxide, key indicators of potential life-supporting environments. These instruments, working in concert, not only pinpoint the location and existence of planets like Gliese 163c, but also provide a detailed look at their atmospheres and possible conditions for life, ushering in a new era of exoplanet discovery. Data interpretation. Interpreting the data received from Gliese 163c is a meticulous process that begins with the initial reception of signals captured by the James Webb Space Telescope. These signals, primarily in the form of infrared light, are analyzed using a variety of computational models to determine the planet's atmospheric composition, surface temperature, and potential presence of water vapor, among other vital characteristics. The accuracy of these findings is paramount. To ensure reliability, astronomers employ several validation techniques. First, the data undergoes a peer review process, where multiple independent teams of scientists examine the findings. This collaboration helps to eliminate biases and verify the consistency of the results, across different observational methods and software analyses. Additionally, the findings from Gliese 163c are cross-referenced with similar exoplanets data, providing a comparative baseline that bolsters the confidence in the interpretations. By integrating these methods, astronomers not only refine their understanding of Gliese 163c, but also enhance the broader scientific community's trust in these distant world observations. Hypothetical life forms. Gliese 163c, with its position firmly within the habitable zone of its star, ignites the imagination with possibilities of life. The conditions on this exoplanet, which closely mirror those of Earth in terms of temperature and potential water presence, lead us to consider what forms of life might thrive there. Picture, if you will, microbial life forms that have adapted to potentially extreme conditions, which could range from intense solar radiation to varying atmospheric compositions. Moreover, the possibility of more complex multicellular organisms cannot be dismissed. These organisms might possess unique adaptations to their environment, perhaps akin to extremophiles on Earth that thrive in the harshest conditions from deep sea vents to the frozen tundras. The presence of liquid water, a critical ingredient for life as we know it, could mean that aquatic life forms might dominate the biosphere of Gliese 163c. Imagine creatures that have evolved not only to survive but to flourish in the alien oceans or lakes of this distant world, developing novel biochemistries that challenge our very conception of life. Each hypothesis not only expands our understanding of biology, but also deepens the awe and mystery surrounding our universe's potential to harbor diverse life forms. What this discovery means. The discovery of Gliese 163c as a potentially habitable planet has profound implications, both scientifically and philosophically. From a scientific standpoint, this finding challenges and expands our understanding of habitable environments. It prompts a re-evaluation of how we study planetary atmospheres and climates, pushing us to develop more sophisticated models to predict and comprehend life-supporting conditions. Moreover, Gliese 163c offers a real-time laboratory for testing theories about planetary formation, evolution, and the potential for sustaining life. Philosophically, the discovery stirs profound questions about our place in the universe. The existence of another potentially habitable planet inherently suggests the possibility of life beyond Earth, which could fundamentally alter our understanding of life's uniqueness and rarity. It encourages us to reflect on our responsibilities as a species and the ethical considerations of exploring and potentially interacting with other life forms. The mere presence of such a planet invites us to ponder our solitude or kinship in the cosmos, potentially reshaping human consciousness and our philosophical outlook on life, existence, and the universe at large. Next steps in research. Building on the groundbreaking discovery of Gliese 163c, the scientific community is buzzing with plans for future missions aimed at delving deeper into this potentially habitable exoplanet. These ambitious missions are designed not only to confirm the preliminary findings about the planet's environment, but also to explore its atmosphere in much greater detail. One of the primary objectives is to analyze the atmospheric composition and look for signatures of gases like oxygen and methane that could indicate biological processes. Another focal point of upcoming missions will be to measure Gliese 163c's temperature gradients and seasonal variations, providing insights into its climate systems. This will help scientists understand whether conditions on the planet could support liquid water, a crucial ingredient for life as we know it. By deploying advanced spectroscopy and imaging techniques, these missions will capture high-resolution data, offering a clearer picture of the planet's surface and potential weather phenomena. Furthermore, astronomers hope to determine the planet's mass with greater precision. This is essential for understanding the planet's gravitational pull and its effect on potential atmospheres. Each piece of data brings us one step closer to answering the tantalizing question: could Gliese 163c be a second home for humanity, or perhaps already home to its own form of life? Through these efforts, we seek not just to discover, but to profoundly understand what lies beyond our solar system. Learning from Gliese 163c. The discovery of Gliese 163c opens up a wealth of educational opportunities and has the potential to significantly boost public interest in astronomy and exoplanetary science. As educators integrate this new information into curriculums, students and the public alike can experience firsthand the thrilling evolution of our understanding of the universe. The concept of habitable exoplanets, such as Gliese 163c, provides a concrete example of how theoretical astrophysics impacts real-world science and stokes curiosity about life beyond Earth. This discovery also serves as an excellent tool for engaging the public in science. Media coverage and popular science content that discuss Gliese 163c can help demystify the process of scientific discovery, making the field of astronomy more accessible and appealing to a broader audience. It allows for interactive discussions, workshops, and potentially even citizen science projects where amateurs can contribute to ongoing research. The excitement generated by such findings can lead to increased funding and support for further space exploration, ensuring that the study of exoplanets remains a dynamic field at the forefront of scientific inquiry. Advanced scientific theories and models. The exploration of Gliese 163c has catalyzed the development of new scientific theories and models that aim to decode the complex environments of distant exoplanets. As astronomers analyze the data gathered by the James Webb Space Telescope, they are beginning to challenge and expand existing models of planetary habitability. For instance, the traditional model that categorizes a planet's potential for life based on its distance from the star is being nuanced with more complex variables such as atmospheric composition, magnetic fields, and orbital stability. These refined models consider how the unique characteristics of Gliese 163c, like its atmospheric chemistry and potential geothermal activity, could support life in ways that differ from Earth. The study of this exoplanet also allows scientists to test theories of planet formation and evolution in the context of different star systems. This not only enriches our understanding of how planetary systems develop, but also widens our search criteria for life-sustaining planets across the galaxy. By integrating observations from Gliese 163c into broader astrophysical models, we are on the brink of potentially discovering new types of habitable environments, fundamentally shifting our understanding of where life could exist in the universe. We hope you found these facts intriguing. If you've heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery. While you're still here, feel free to click on other videos you will see on your screen right now.
When you get a solar flare, the level of charged particles can be so high, it can short-circuit the electronics of satellites when it reaches Earth.
Imagine witnessing the power of millions of nuclear bombs exploding simultaneously. That's the staggering energy released by a solar flare, nature's most magnificent and terrifying display. As the sun belches out these colossal bursts of plasma, we're reminded of our star's formidable power. In this video, we dive into the heart of solar flares with none other than astrophysicist Neil deGrasse Tyson, guiding us through the cosmos' fiery wrath. What happens when these cosmic giants target Earth? Are we prepared for the potential aftermath?
Scientists, some, are sounding the alarm on a so-called solar superstorm that could, and this is important, eventually wipe out the internet for weeks or even months.
Understanding solar flares. Solar flares stand as colossal explosions on the sun's surface, far from being mere flickers or insignificant bursts. These events represent moments when immense amounts of magnetic energy are converted into heat, light, and a spectacular expulsion of particles. To grasp the scale of energy unleashed during a solar flare, imagine the simultaneous detonation of millions of nuclear bombs. This comparison, while staggering, actually captures the magnitude of energy released in the process. The extraordinary energy from a solar flare doesn't just vanish into the cosmic void. Instead, it has the potential to reach Earth, affecting our technological infrastructure, the planet's atmosphere, and possibly even altering our way of living. But what triggers these powerful solar outbursts? The genesis of solar flares lies deep within the sun's core, amid the chaotic dance of magnetic fields. In this volatile realm, magnetic lines of force undergo realignment, releasing energy on a scale that is hard to comprehend, giving birth to what we witness as solar flares. The impact of these solar explosions extends across the solar system, sending a flux of energetic particles in Earth's direction. These events underscore the immense power of our closest star and its profound influence on our everyday life and the fragile equilibrium of our planet. As observers of these celestial spectacles, often likened to solar fireworks, we are constantly reminded of the delicate balance that enables life to flourish on Earth under the watchful gaze of our ever-dynamic sun. The sun's red giant phase. In the distant future, a monumental transformation awaits our sun, marking a pivotal moment in the vast timeline of the cosmos. This future phase, known to astronomers as the red giant phase, heralds a significant shift in the sun's existence and spells a dramatic conclusion for life on Earth. During this period, our sun will undergo a dramatic increase in size, expanding to engulf the inner planets of the solar system, including our own planet, Earth. As the sun depletes its nuclear fuel, it is set to grow to a gargantuan scale, ballooning to hundreds of times its current diameter. Its outer layers will stretch out, reaching the very orbit of Earth, bringing about profound and unimaginable changes to our home planet. The intensifying heat and radiation from the sun, now a vast and all-consuming giant, will lead to the boiling of Earth's oceans, which will evaporate and vanish into the void of space. The Earth, once a vibrant blue orb teeming with life, will be transformed into a desolate, barren rock, devoid of any life-sustaining water. This cataclysmic transformation will signify the end of the Earth's capacity to harbor life. The planet's atmosphere will be gradually stripped away, leaving its surface exposed to the scorching effects of the sun's radiation, turning it into nothing more than a scorched wasteland. This inevitable phase in the sun's life cycle serves as a stark reminder of the transient nature of celestial bodies and the ultimate destiny that awaits our planet. It underscores the profound impact of cosmic evolution on the fate of Earth, highlighting the impermanent nature of our world in the grand scheme of the universe. The Carrington Event, a historical perspective. In the midst of the 19th century, humanity stood witness to an extraordinary cosmic phenomenon that profoundly influenced our burgeoning technological landscape. This event, now known as the Carrington Event, occurred in the late summer of 1859, marking a significant milestone in the annals of space weather research. It derives its name from Richard Carrington, a dedicated British astronomer who meticulously documented the solar flare that was at the heart of this unprecedented event. On an unremarkable day, amidst his regular observations, Carrington observed an intense white light erupting from the surface of the sun. This was not merely a spectacle of light and energy, it was the harbinger of an immense geomagnetic storm that would reach Earth about 18 hours later. This storm unleashed a magnetic wave across our planet, the likes of which had never been documented in the annals of human history. The effects of this geomagnetic storm were both immediate and profound, particularly on the telegraph systems of the time. These systems represented the pinnacle of communication technology in the mid-19th century, but they were ill-prepared for the solar storm's impacts. Telegraph operators were startled by papers catching fire, machines functioning without any external power, and electric shocks that rendered the telegraph network erratic or, in some cases, completely inoperative. This event served as a stark reminder of our technological vulnerabilities and the potential havoc that solar activity can wreak on human advancements. Modern dangers of solar flares. As we delve deeper into an era where technology is not just a part of our lives, but the foundation upon which our modern society is built, the shadow of solar flares looms larger and more ominously than ever before. These natural phenomena, eruptions of immense energy from the sun, pose a significant threat to the technological infrastructure that underpins our way of life. Envision a scenario where our world is plunged into darkness, not just momentarily or for a few hours, but for an extended period that stretches into days, weeks, or possibly even longer. This scenario is not plucked from the pages of a science fiction novel, but represents a real and present danger in our technologically dependent age. The electrical grids, the lifelines of our civilization, are alarmingly susceptible to the destructions caused by solar flares. A substantial solar flare could unleash electrical currents powerful enough to destroy transformers and incapacitate power stations, casting vast swaths of civilization into an unwelcome return to darkness. The risks extend far beyond the vulnerabilities of our terrestrial infrastructure. The skies above, crowded with satellites, are integral to nearly every facet of modern life, from navigating our way through cities to the seamless flow of global communications. These satellites are at peril from the intense burst of energetic particles from solar flares, which can wreak havoc on satellite electronics, disturb the transmission of signals, and cause deterioration to these critical orbital assets. The potential for a domino effect of failures is real, with consequences that could cascade through every corner of our economy, disrupt emergency services, and affect many other critical aspects of our daily lives. Furthermore, our global communication networks, the very threads that weave together the fabric of our interconnected existence, stand on precarious ground. The impact of a solar flare could instantly sever these connections, disrupting the flow of information and communication on which we have become so dependent. A recent incident, a significant solar flare causing a moderate radio blackout over South America, starkly illustrates our system's vulnerability. Such events underscore the precariousness of our reliance on technology, highlighting how quickly our capabilities for communication, navigation, and digital operation can be disrupted. In this light, solar flares represent not just a natural curiosity, but a formidable challenge to the resilience of our technological society, reminding us of the need for preparedness and protection against the caprices of our sun. Solar observations and advances in astronomy. In the vast expanse of our universe, the sun has always been a focal point of human curiosity and scientific inquiry. Our journey into the realm of solar astronomy began in earnest in the early 18th century, when astronomers first turned their telescopes towards the heavens, not just to map the stars, but to study our own star's enigmatic and vibrant nature. This was a time when the field of solar astronomy was as straightforward as it was daring. Armed with nothing but their telescopes and the naked eye, early astronomers began to peel back the layers of the sun's blazing facade. The sun, a seemingly eternal flame in the sky, revealed its secrets slowly. By simply observing its light, early scientists learned volumes. They used prisms to dissect the sunlight into its many wavelengths, unveiling a spectrum that stretched from the ultraviolet to the visible and into the infrared. They discovered sunspots and solar flares, dark and light phenomena that danced across the solar surface, hinting at the immense energy and complex processes at play. These initial observations laid the groundwork for our understanding of the sun and its impact on Earth. As the centuries progressed, so too did our technological prowess. The advent of the telescope brought the cosmos closer, but it was the evolution of solar observatories and space-based telescopes that marked a new era in solar astronomy. The mid-20th century saw the launch of the first satellites dedicated to observing the sun, providing a vantage point unobstructed by Earth's atmosphere. This was a quantum leap forward, offering us a continuous view of our star in multiple wavelengths, day and night. In the 21st century, our quest to understand the sun has led to the development of cutting-edge observatories equipped with instruments so precise they can measure the magnetic fields and plasma flows of the sun's surface and beyond. The Daniel K. Inouye Solar Telescope, for instance, stands as a titan among these modern marvels. With its unparalleled resolution, it allows us to observe the sun's magnetic field in exquisite detail, offering insights into phenomena like solar flares and coronal mass ejections with unprecedented clarity. Moreover, the Parker Solar Probe, launched in 2018, is on a daring mission to touch the sun. Well, almost. It aims to travel closer to the sun's surface than any spacecraft before it, braving extreme temperatures and radiation to gather data that could solve long-standing mysteries about the sun's corona and its influence on space weather. The threat of coronal mass ejections. In the cosmic dance of celestial forces, the sun plays a pivotal role, not just as the source of light and life, but also as a harbinger of potentially catastrophic phenomena. Among these are the coronal mass ejections, or CMAs, vast expulsions of plasma and magnetic fields from the sun's corona, the outermost part of the sun's atmosphere. While solar flares are intense bursts of radiation that can light up the Earth's sky with dazzling auroras, CMAs are a different beast altogether. They release huge bubbles of gas and magnetic fields into space. When these bubbles strike the Earth, they can cause geomagnetic storms capable of wreaking havoc on our planet's magnetic field. The difference between solar flares and CMAs is not just in their nature, but also in their impact. While solar flares affect Earth's atmosphere in the form of electromagnetic radiation, CMAs carry with them the physical matter from the sun, which can interact with Earth's magnetic field in more profound ways. This interaction can lead to severe disturbances in the geomagnetic environment, known as geomagnetic storms. The potential for CMAs to cause extensive damage to Earth's infrastructure is not a matter of speculation, but a reality we have glimpsed in historical events. The charged particles from these ejections can induce electric currents in power lines, leading to widespread power outages and damaging transformers and other vital components of the electrical grid. In an age where our society is ever more dependent on technology and electrical power, the threat posed by CMEs extends beyond mere inconvenience. A powerful enough CME could disrupt communication networks, GPS systems, and even lead to the failure of critical infrastructure such as water supplies and transportation systems. The Sun's magnetic field and its effects. The Sun's magnetic field is a complex and dynamic feature, far from being a uniform or stable presence. It comes to life due to the roiling, convective movements of plasma that churn beneath the Sun's surface, creating a magnetic field that is both powerful and changeable. This field is at the heart of the Sun's periodic bursts of energy, which we see as solar flares and coronal mass ejections, CMAs. However, the mechanism that triggers these powerful events is a subject of fascination and study. At the core of these explosive phenomena is the process known as magnetic reconnection. To visualize it, think of the Sun's magnetic field lines as strands of energy that are constantly moving, intertwining, and evolving. Occasionally, these lines can break and then reconnect in different arrangements. When they do, they release a tremendous amount of energy in a short time. Magnetic reconnection acts as the trigger for solar flares and is the force that launches CMAs into the vastness of space. The impact of these solar events goes well beyond the confines of the Sun. Solar flares emit intense radiation that can disturb the Earth's atmosphere, leading to disruptions in satellite operations and communications networks. The threats from CMAs are even more significant. These gigantic clouds of plasma, when thrown into space, can have dramatic effects if the Earth is in their trajectory. The consequences range from the creation of spectacular auroras to intense geomagnetic storms. Such storms have the potential to damage our electrical grids and technological systems, highlighting the profound influence of solar activity on our daily lives and the technology we depend on. The latest solar flare event. In an unexpected twist in the saga of celestial phenomena, the Sun recently demonstrated its formidable power by releasing its strongest solar flare in almost 2 decades, an event that has become a landmark in the study of solar activities. This massive explosion of electromagnetic energy, categorized as an X2.8 class flare, has not only riveted the global astronomical community, but also highlighted the Sun's capricious nature. Originating from a dynamic sunspot labeled AR 3514, the flare blasted through the cosmos, serving as a vivid testament to the immense influence of solar phenomena on our technological realm. The effects of this solar flare were swiftly felt on Earth, manifesting as a moderate radio blackout across South America. This incident served as a stark indication of our fragile standing in the face of the Sun's unpredictable temperament. Moreover, this solar event adorned the skies with magnificent auroras, which stretched well beyond their usual geographic bounds, providing a stunning spectacle of natural beauty. Despite the awe-inspiring visuals, these occurrences bear a cautionary note regarding the potential destructions that such solar activities can pose to our deeply interconnected global systems, reminding us of the delicate balance between technological advancement and cosmic forces. Preparing for future solar storms. In anticipation of future solar storms, scientists and researchers have embraced a comprehensive strategy that includes early detection, a deeper understanding of solar phenomena, and the development of effective mitigation plans. This strategic approach is greatly supported by the deployment of cutting-edge solar observatories, which have vastly enhanced our capability to predict and brace for solar events. Among these advancements, the National Science Foundation's Daniel K. Inouye Solar Telescope stands out as a significant milestone in our observational efforts. Equipped with the latest scientific instruments, including 4 spectropolarimeters designed to measure the Sun's magnetic properties, the DKIST offers invaluable insights into the intricate magnetic field of the Sun, spanning its corona, chromosphere, and photosphere. These state-of-the-art observatories play a crucial role beyond mere observation. They act as an advanced early warning system for our planet. By analyzing the magnetic field of coronal mass ejections, CMAs at the moment they occur, scientists can determine the direction and potential impact of these charged particles. This is vital for assessing whether the ejected material will pose a threat to Earth. Armed with this knowledge, we can predict the arrival of solar storms well in advance, providing a precious window for taking protective measures. These measures are aimed at safeguarding critical infrastructure, including our electrical grids, communication networks, and satellites from the potentially devastating effects of solar storms. Moreover, the focus on developing and refining predictive models of the sun's behavior has become increasingly important. These models, powered by the wealth of data collected by solar observatories, are crucial for improving our understanding of solar dynamics. They enable scientists to predict solar activities and storms with a higher degree of accuracy, making it possible to anticipate and mitigate the impact of these celestial events on Earth. This multifaceted approach exemplifies the proactive steps being taken to protect our planet from the powerful forces of our closest star, ensuring a higher level of preparedness for future solar phenomena. In confronting the unpredictable fury of solar storms, humanity's resolve shines as brightly as the phenomena we seek to understand. Leveraging advanced observatories and scientific ingenuity, we stand prepared, not just to withstand the sun's might, but to thrive in its presence. This commitment to foresight and resilience illuminates our path forward, ensuring that as we gaze up at the cosmos, we do so not with fear, but with the confidence of those ready to meet the future. We hope you found these facts intriguing. If you've heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery. While you're still here, feel free to click on other videos you will see on the screen right now.